prayers. Okay, so we will start with our today's session. Our first resource person, our first speaker is Dr. Ragini Raghav, and she has more than 5 years experience of teaching in the field of spectroscopy, analytical techniques, nanotechnology. Okay, so I think you will grasp as much as you can. So I will welcome Dr. Ragini Raghav to take your lecture.
Hi, good afternoon, everyone. I hope I'm audible. Right. So I'm going to take a lecture on spectroscopy. Right. So the outline of the presentation will be we'll try to cover up maximum spectroscopy that we can, which are important from the a competitive exam perspective. Right. So we'll talk about basics of spectroscopy. Then we'll take UV visible spectroscopy, atomic spectroscopy, which would include AAS, AES, and MS, and FTIR and Raman spectroscopy, CD and ORD and NMR. Finally, right. So essentially, when we talk about spectroscopy, it is nothing but how the light interacts with matter, right? And when I say light, what I mean is the whole EM radiation spectra, which means I'm starting from gamma rays and ending with radio waves. So however, all the waves have different wavelengths or different frequencies, and they interact with material differently, right? In the sense, UV visible spectroscopy, in a very layman term, visible spectroscopy is for something that has color, right? And for if I say X-ray spectroscopy, it is something for very fundamental thing like molecular atomic arrangement, right? So spectroscopy is nothing but studying how light interacts with matter, right? So essentially, most of them have a basic fundamental model very similar to each other instrumentation wise. The only changes happens with the source of light, right? If you need X-ray, you need another source, and in between the filters are different, right? So basic instrumentation remains the same, but the changes in the sense of the source and the sample and the analyzers, it differs, right? So if we talk about what is exactly EM radiation, EM radiation is electromagnetic radiation which has both properties of wave and particles. This you would have studied several times since your school, that light behaves in both manner, as a wave and as a particle also. When we talk about EM radiation and when we talk about interaction of light with matter, we consider both the forms, in the sense how waveform interacts with matter and how particles interact with matter, right? So essentially, if you see, EM radiation is you have a magnetic field and an electric field which is perpendicular to each other, and it flows in a direction, right? Now this is a schematic representation, the GIF file that you can see, to show how EM radiation actually flows through, right? Now this, I think you must have known, but we'll discuss it again. The light, usually when we study about spectroscopy, we consider three main important things: how the light is reflected, how the light is absorbed, and how it is transmitted, right? So most of them are based on these three fundamental things. If the particle is absorbing light, or it is reflecting it back, or it is transmitting, right? So quickly, let's take how light interacts with matter. So reflection, as you all know, you can see your reflection in the mirror. It's nothing but light getting back at an angle, right? Refraction is bending of light and change in its direction. The best example is putting a pencil in water. You can see the direction changes, so you see the split in the pencil, right? The third is deflection. Deflection is deflecting it to another angle. Here the angle was same, right? Here it differs, and here also it differs. The alpha will never be equal to gamma. So actually you're deflecting your light, right? Then diffraction, something that you see when you're clicking pics in your camera. When the light has to pass through a very small slit, बहुत छोटे से hole के through, when it has to pass through, it diffracts, right? So essentially your light component is getting split into different colors. Scattering is something that you see, again, a real life example. If you have a very small slit of the window open in your room, you can see light scattering those dust particles, right? That is scattering essentially. Or you can see it even when you try to put a torch in front of a glass of water which has little solid particles. You'll see light dispersing off. That is scattering. Absorption is the reason you see colors, right? In the sense why the plant is green, or why whatever color that you wear in your clothes, why you can see that. It's because it is absorbing the rest of the colors and reflecting back just the single one. Emission is when the light is getting absorbed, and on excitation, it gives back the energy in terms of photons. So it is emission. Then fluorescence is something that you have already dealt with in the sense of fluorescent molecules, which absorbs the lower wavelength, higher energy light, and reflects back greater energy. It's like ETBR. You give it 330 or 380 nanometers in light in UV form, and you see a orange color band, right? ETBR. The last is phosphorescence. That is glow in dark stickers that you must have seen. You give it light, and it saves the light for a very longer time and disperses it at smaller intervals. So that is the reason the energy is dissipated at a very longer time, right? Now essentially we deal with almost all of them except from phosphorescence, because it is difficult to quantify it and qualify it. Rest everything we'll be using in spectroscopy, right? So if you see the basic molecular and atomic transitions that occur due to EM radiation when it interacts with matter, gamma will give you nuclear transitions, and gamma is difficult to control and very hazardous. So normally we don't deal with gamma, right? We start with X-ray. X-ray has core level electronic configuration changes. So when you have to know what is the lattice arrangement of a molecule, you go for X-rays, right? You use XRD or X-ray crystallography. When you use UV visible spectroscopy, that is for valence electrons, right? Outermost electrons that are responsible for absorbing energy and then dissipating it back, right? Then infrared is very superficial. It would because as you go down, the energy decreases, right? This is maximum energy, this is minimum energy. So when you go to infrared, the energy is very low, so it's superficial in the sense just molecular interaction or vibrations will be recorded, and you can actually estimate what is the estimate the bonds between two molecules, right? Now you use infrared for Raman spectroscopy and FTIR, Fourier transform infrared spectroscopy. Then the next one is microwave. Microwave is for normally ESR, electron spin resonance, and finally radio waves, that is for nuclear spin resonance, right? So we'll start with UV visible spectroscopy. As I've already told you, the atom at a ground state will absorb energy, a particular amount of energy, and go to excited state. When you record how much energy it has absorbed and reach the absorption excited state, this is called as absorption spectroscopy. And when the atom absorbs energy and comes down, giving back the photon that it had absorbed, the same energy, that is called as emission 1, right? So UV visible spectroscopy, when we are dealing with biological molecules, is just going to show you N to pi star and pi to pi star transitions. Now what I mean is, you've already read this in chemistry. These are bonding and non-bonding and anti-bonding orbitals, right? So UV and visible, these lights do not have this ability or the amount that is responsible for pi to pi star excitation or N to pi star, right? So in biological molecules or in UV visible spectroscopy, we normally have N to pi star and pi to pi star transitions that are responsible for absorption, right? So what it means is, if you say UV, that means N to pi star means any, or pi to pi star means anything that has a double bond will be UV active, right? Irrespective of the color of it. If it has color, that means it is visible spectroscopy active, right? If you have a visible color, then normally we call them chromophores, and then you might get two peaks if the compound is double bonded and has a chromophore, or it might be just pi to pi bonding wala, that is let's say benzene. Benzene is colorless, but still it is UV active, right? So if you see the transition, like I've already told you, pi to pi star, normally alkenes and alkynes, and N to pi stars for carbonyl compounds, right? So HOMO and LUMO, I think you must have read it, but then I'll give you a glimpse of it. LUMO is lowest lowest unoccupied molecular orbital, and HOMO is highest occupied molecular orbital, right? So the transitions between N to pi star and pi to pi star, see, all the transitions are possible, but it depends on the amount of energy you're giving it. If it was not UV visible and if you were giving it X-ray, probably N to pi star was possible for it, right? Because pi bonds, they are more stable, while sigma bonds are more stable, while pi bonds are a little lesser in energy, and they'll absorb lesser amount of energy and then get excited. So the principle of UV visible spectroscopy is Beer-Lambert's law, right? You must have already read it. So the Beer law is that intensity of the monochromatic light decreases exponentially with concentration, right? And Lambert's law says it is dependent on the path length. So we got a absorption that was directly proportional to concentration, and absorption again directly proportional to the path length. So we got A is equals to E into C into T, right? E is the molar extinction coefficient, which normally is depend on the how strongly the chemical species absorbs the wavelength. This is the instrumentation. You usually have two different lamps, or you can have a single xenon lamp which gives you both UV and visible spectra, right? So you have a filter, you have a monochromator. Monochromator has the ability to just filter the light into a single wavelength, right? Monochrome, single chrome, single color essentially. Then you have a beam splitter that will actually split the light into two different parts, right? without changing the intensity of light. So what happens is, if eye goes here, beam splitter will make it 2 eye, and then 1 eye will go from here and 1 eye will go from here. Now this is a standard diagram from double beam spectrophotometer, which you use normally. Single beam spectrophotometer, you'll have to keep adding reference again and again and then sample, right? So this is a double beam spectrophotometer, so the eye will go over here and one part of the light eye will go over here. Reference to sample, you can collect the changes according to reference, which you normally do it in your labs also, right? You put a blank, you set the baseline, and then you take your sample, which is colored or non-colored, UV active, and then you record what is the change with reference to the blank you have set. Now, in biological systems, if you see proteins and nucleic acids, essentially we do 260 by 280, right? So essentially for protein estimation or nucleic acid estimation, you use UV visible spectroscopy. Now, peptide bonds essentially are active for at 190, that is UV region, again at 210 nanometer, again a UV region, right? So if you relate to it, anything that has a double bond is UV active. So if there is a peptide bond, it will be UV active, irrespective of it has color or it does not have a color, right? So amino acids, if you see what happened was, if you see individually amino acids, they have a different absorption maximas. Phenylalanine has 257, tyrosine has 274, and tryptophan has 280. But it was universally decided that we'll take protein maxima at 280. So what happens is, if it is a reference point, it becomes easier universally to estimate it, right? So we have selected 280 for proteins and 260 for nucleic acid, although if you see, purines do it for 260 and pyrimidines do it for 275. So to normalize the thing all over the universe, what we did was we did it for 260 to 280. However, if you see individually, they will always have a different maxima, right? So other important thing that you have to remember is that factors that affect UV visible spectroscopy. Now, essentially what happens is, sometimes you take a UV spectra and the maxima is 260. And if you take the graph, probably the maxima doesn't come up to be 260. Now, this can happen because of protonation and deprotonation, solvent polarity, or orientation effects of a molecule, right? If the maxima shifts to your right hand side, if you see wavelength, it would be violet to red, right? Violet has the least and maximum energy, and red would have the least energy, right? So if it shifts to the lower energy region, it is called as red shift, or scientifically you have to remember it's called bathochromic shift. If it shifts to your left side, that means blue shift, that is, it is moving towards blue direction, it's called hypsochromic, right? Now, why this would happen is, essentially, if you have to imagine it like, if the excitation is occurring at lower wavelengths, that means energy uske paas already thi. That means the molecule somehow was already in an excited state and it had already a part of energy, and the rest of the part was, attained by UV visible light that was given by the source. So agar protonation deprotonation ki tarike se dekhte hain, if the proton cloud is already moving around for forming bonds, or is attracted for some reason, or has a redox potential, so what will happen, it will already have an initial energy, so you'll require lesser energy to excite it. So that is the reason it would come at lower energy region. However, if the bond with, let's assume, the solvent is very high, you have a highly polar molecule and you've dissolved it in a very polar solvent, so what will happen, they both will be engaged in forming bonds. So to break that bond and give them energy and make it excited, it has to take more energy from the system, right? So that would give you higher energy shift, so that would be blue shift. Then comes hyperchromicity and hypochromicity. If you see orientation of the molecules, if it is amino acid, all the surfaces are available for absorption, right? So that is the reason, if you are taking absorption of amino acid, it would be greatest, right? Right. So this is called as hyperchromicity. If you take it for peptide, one side we have blocked, right? So only one side is not available for the UV light to be exposed. So essentially your graph would come over here, the normal one. If it is a protein, now it has formed a structure and it is closing a lot of surface areas, right? So a lot of surface areas are not exposed anymore for light to be absorbed. So that results in hypochromicity, right? Now these four things you have to remember: redshift, blue shift, hyperchromicity, and hyperchromicity, right? So we use UV visible spectroscopy for identifying of functional groups, impurity, qualitative assays, and quantitative. Qualitative and quantitative, I think you must have been dealing them within your labs mostly, right? Like you make BSA standard curves, right? For 280 nanometers. So essentially qualitative, quantitative, impurities for detection and for functional group detection. Next, we come to atomic spectroscopy. Atomic spectroscopy essentially means atomic level where we are trying to check things, right? So it is divided into three parts: atomic absorption spectroscopy, known as AAS, atomic mass spectroscopy, that is MS, and atomic emission spectroscopy, that is known as AES, right? So atomic absorption spectroscopy was given by Sir Alan Walsh in 1954. Nearly 62 elements can be identified using AAS, right? Essentially, that means if you have a sample and you want to detect a particular amount of sample or identify a single element, you can do it with absorption spectroscopy. This is something that was not possible with UV visible spectroscopy. UV visible spectroscopy does not have an ability to distinguish between elements, right? So if you see the schematic representation of the instrument, you have a light source. Now, because you're dealing it within an atomic level, so UV visible, you know, it is just pi to pi star and n to pi star. So you need to break bonds. अब आपको pi bonds के साथ साथ sigma bonds भी break करने पड़ेंगे, because you need to analyze your sample in a atomic level, right? So you obviously need a higher energy, which we provided with tungsten filament, right, which gives you an electron beam. So you have your sample which gets which is dissolved into a solvent, and then you form a aerosol for it and then flow it through your source, which further gives it more energy and breaks it down to atomic levels. Then the light passes through the tungsten filament. Whatever energy is required by the sample, if it absorbs, you can see from the spectra, they disappear from the spectra, right? So if what it means is, if let's assume it's an hydrogen, this is for a hydrogen. So let's assume for the transitions, let's assume the light has been absorbed in red region, orange, yellow region, green region, and blue region. So that light would be missing, and that is quantified using a photomultiplier tube, that what amount of light was missing from your spectra, right? So that is the reason this is called as discontinuous spectra, while in UV visible spectroscopy, it is a continuous spectra, right? So you have a lot of light sources and atomizers for your AAS. You have a hollow cathode lamp, right? Atomizer, you have two different ones. That one is flame one, like we showed you in the diagram, right? This is a flame one. You can use a graphite furnace tube also. The mechanism is the same. It has to provide you heat at a very high temperature so that your sample dissociates into atomic levels. And finally, you have a detector, which is a photomultiplier tube. Photomultiplier tube has an ability to just amplify your signal. So if it is just one electron that is achieved at the detector, it would still multiply it, amplify it, and give you a readable output, right? So next is atomic emission spectroscopy. Emission is very similar to what we did in absorption spectroscopy. The only difference is that you don't need a light source. Why? Because you're giving it energy, and now it has to give the excited energy and tell you where the bands are, right? So essentially, absorption spectroscopy mein, the bands miss from the regular spectra because it has been absorbed by the sample. In emission spectroscopy, the bands appear in the spectra over a black background because the energy is now being released, right? If the sample gets excited at that particular energy, it would give you lines according to that photon emitted, right? So the first, that was the light source, is just missing. You have different types of you have different like flame or ICP, inductively coupled plasma, DC, AC, or spark generated. Now these are all the sources that are available that would actually break the bonds and make it into elemental, right? So the sampling and sample preparation is the same, and the next section for detection is also the same as of AAS, right? For atomic emission, you might have to remember the temperatures, right? Mostly ICP, inductively coupled plasma, AC/DC spark, and spark. They all have almost the same temperature. Because of the higher temperature, the sample dissociates into atomic level, right? It is normally visible through naked eye also, like it is in the like it is in fireworks, right? According to the doping that you do, you can see the color of it. So in flame, the color of the flame will change according to the element. Essentially what it means is, if you have put your sample and it has a lot of potassium, your the color of the flame would turn lilac, purplish, right? If it has a lot of lithium, it would turn into pinkish. So according to the color of the flame also, you can, identify it. It is very similar to flame photometry, just that you have a very high temperature and you can quantify it. It becomes AES, right? Atomic emission. Next we come to mass spectroscopy. Mass spectroscopy is again atomic level changes. That is, you tell what is the mass to charge ratio, or how much amount of an entity is present in your molecule, right? So what happens is, when you have an electron, outermost electron, it will get knocked off. So when the electron gets knocked off, because of +1 charge, you will have a daughter molecule which has a +1 charge, right? Now sorry, you have a daughter molecule which has a +1 charge. So in mass spectroscopy, we imagine it that every molecule will have just one electron removed. So mass to charge ratio would be always Z, mass to charge, M by Z. Z would always be +1 because you have removed one electron. So according to mass, the separation would occur. इससे पहले वाले स्पेक्ट्रोस्कोपीज में we were not dealing with mass, we were dealing with essentially elemental analysis, right? Or the prosthetic groups present, or the bonding, right? Now what we are talking about is, we are talking about what is the size of your molecule, right? So to identify what is the size of your sample, right, you have to do mass spectroscopy. Now we have a lot of procedures in mass spectroscopy to identify the molecule. But if we talk about biomolecules, we cannot actually give them a very high temperature, because they will actually you will just ruin your sample. So essentially, neither you can give them very high energy directly, nor you can put them into very high temperature. So essentially what we do is, for mass spectroscopy for biomolecules, we use a term that is called as technique that is called as MALDI. That is matrix assisted light desorption ionization. Now what it means is, what it will do is, you don't give your sample directly the amount of energy. Imagine if you give electron beam to your biological sample, it would not be stable. First, it would just burn out and you will not get anything out of it, right? So essentially what we do it, we take a matrix and we put our sample into that matrix. Now the matrix is such that the energy is provided to the matrix, and in terms of energy, that gets transferred to your biomolecule. So it is not a direct transmission of energy, it's actually an indirect manner. The laser will give the energy to the matrix, and the matrix will slowly provide the energy for excitation to your biomolecules till they form a +1 charge daughter ions, right? The analyzer, if you see the instrument, you have an ionization unit which turns into molecular ions, which I've already told you, +1 charge. The size is different, so you can see 2 are bigger and 2 are smaller. Now then they are flown through a detector. Normally a detector there can be different types of detectors. Essentially, this is a diagrammatic representation of TOF. TOF is time of flight. Usually MILDI is taken up with TOF because it gives you better sensitivity and better results, right? So essentially what will happen is, you'll provide ionization. Once the electrons are thrown out of the atoms, you'll get +1 charge proton ions, right? Positive ions, and these positive ions are flown through a time of flight. That is a tube which does not have any electrical conductivity. It just has to reach the end point, right? So you have put your polarity at the end and nothing else. So what will happen is, they'll slowly start moving, and because the drag force in case of bigger molecules is more, the smaller molecule will reach first and then the bigger molecule will reach, right? So you have a lot of procedures for ionization for chemical things, right? I'm not talking about biomolecules, I'm talking about chemical entities. Chemical entities where you can use electron impact, electron spray, chemical ionization, plasma desorption, fast atom bombardment, thermospray, and MALDI, right? Now essentially first 6 months you can use it for any molecule, 7th is exclusively for biomolecules, even 5th one, fast atom bombardment. If there is a question that what you can use for, what ionization technique you can use for actually biomolecules, if you don't see MALDI, don't panic, it must be fast atom bombardment, right? So other than these, nothing is used for biomolecules. Similarly, for mass analyzer, like I've told you, MALDI is normally associated with time of flight. Ion impact can be associated with quadrupole or ion trap, right? So you have to actually remember the names so that you know what are the mass analyzer that are available in mass spectroscopy. The detector finally, which would detect these ions coming up to it, would be photomultiplier tube, electron multiplier tube, or a Faraday cup, right? Photomultiplier, you can imagine it like photons. You hit it once with a one single photon, it will amplify and give you a amplified signal. Electron multiplier tube, it would actually be the similar to what is a photon multiplier tube does. It would just amplify your signal. Faraday cup is also, it traps the molecules and then gives you a result. You don't have to go in details, you just have to remember the names for the detector. So this is the cartoon that shows the time of flight. What happens, they all will start at a point, at the same point, and slowly the drag force because at the bigger size the drag force is more, so they'll lag behind and the smaller molecules will run off fast, right? Right. So the next one is quadrupole, because quadrupole is frequently asked in paper, right? So I just wanted to tell you in a single cartoon what happens is quadrupole, it means quadra, that is four poles, right? And the opposite one has the same polarity and these keep circulating, right? So what happens is only one single type of atom is allowed, ion is allowed to pass through, rest all of them are discarded, and then it reaches the detector, right? So whatever you are deciding to be analyzed, that only single type of ion would get recorded, rest everything will be discarded off from the quadrupole, right? Then the next one is Fourier transform. Now what we have done is we have done UV visible, which tells you the color or the pi bonds, right? Then we have done atomic, which tells you the elemental analysis or which tells you the mass of the your molecule, right? Now we'll talk about Fourier transform infrared spectroscopy, which will tell you how the bonds have been made, right? See, UV will tell you, okay, there is a pi bond, right? And AS and AES will tell you what element is present. Mass will tell you the exact configuration, okay, C6H6O6, right? So this is the molecule that is present that you have come up with. Now how they are linked together and what is the possible configuration of the molecule, that you have to identify it using Fourier transform. Like you have a thumbprint, everybody has a different thumbprint. Similarly, UV spectra at each bond, in the sense C to C bond in presence of other atoms, has a very distinct absorption spectra, right? So similarly, all the bonds, they have a very distinct type of stretching and bending configuration, which we calculated using Fourier infrared spectroscopy. Now it works at 700 to 225 micrometers. Now to remember this, easiest way is we are going from UV to visible, right? And visible ka last is red, and red ke next becomes infrared. So red normally we take it from 700 to 800. So it starts from 700 and goes to 25 micrometers, right? So essentially the energy would be very less. So only the penetration over the surface ions would happen, surface groups will happen. So that is the reason it is used for transition of vibrations, right? How your bonds are vibrating, you're calculating that, right? So essentially we have a formula for it. Any molecule will have 3n minus 6 fundamental vibrations, except for for a linear molecule, which will have 3n minus 5. You can calculate the fundamental vibrations using this, right? 3n minus 6, that's the thumb rule, right? If it is 3n minus 6, that means it will have 2n minus 5 bending and n minus 1 stretching, right? Stretching and bending means what it means is Stretching essentially means either it's symmetric or it is asymmetric, right? So there are just two possibilities for stretching. So that is the reason it is n minus 1, right? So it can be either symmetric or it can be asymmetric. For bending, we have 4 different types of bending. That is 2n minus 5 I'm talking about. Scissoring, rocking, wagging, and twisting. Now you have to remember the name even if you don't remember how they are happening, right? Which bond is moving which ways. Although it is very easy to understand. However, if you don't remember it, still you have to remember the names of them. Scissoring is, it's like scissors, it's cutting, right? Rocking is going in a same direction. Wagging is out of the plane. That is, it is coming, if you see, out of the plane in front of you. Twisting is again a modification of wagging, where one side is coming out first and second side is coming out later, right? So essentially we have 3n minus 6 molecular vibrations, of which 2n minus 5 are bending and n minus 1 is stretching. Stretching is symmetric and asymmetric, and bending we have 4 different types. So if you see the instrument is very simple. You just have a laser source, right? And it splits the light into 2 different parts, right? Again, a beam splitter, 2I by 2. So one part goes here, one part goes here. Now once of the mirror is stationary and the other one is moving. Why this happens is because this is an interferometer. What it does is it creates a path difference, and the path difference creates the difference in the intensities of light, and whatever is recorded from this interferometer is given to the sample as a whole. Rather than giving it as a beam of energy, what you do is you give it as a packet of energy, which is full of energies of different intensities. Your sample then will vibrate at absorbing every energy that it has been provided with, and your pyroelectric detector will give you a output of what energies has been absorbed. Now why we are doing this is because essentially if you give your molecule higher energy, rather than focusing on molecular vibration, it will start to either absorb energy and go into another excited state, and the purpose of your study, that was molecular vibrations, will be completely lost. So what happens is you have to give it all the energies as a whole. Whatever energy it has to utilize for vibrating, it will absorb, and rest of the energy will be given back as same as in your spectra, right? So essentially why we call it as in Fourier transform is, normally what you get out of the output is interferogram, which means volts per unit, right? So you get something like this. Now this is not so readable. So what happened was, there is a mathematical expression that is known as Fourier transform. You apply it at every single data point and you get a readable output. Now this appears something like that. You have done it in UV visible spectra, right? So it has peaks and dips. Now this is essentially a absorption spectra. So you have dips. Whatever is absorbed has a dip, right? So these energies have been absorbed, and these are characteristic for the bonds, right? Like if you have a bond, if you have some dip at 1100 nanometers, that possibly means it has a OH bond, right? If you have a 3 peaks, that normally means it has a C double bond O, right? So accordingly you have a catalog according to which you can identify what bonds are present and which atom is linked to which atom, right? Similar to what we did in FTIR, it's a extension of FTIR. It's known as Raman spectroscopy, and Sir C.V. Raman got a Nobel Prize for this spectroscopy. Why? Because according to FTIR, 99% of the light was absorbed, right? In the sense utilized. But there is just one single problem, that 1% light that was not utilized was never contemplated what happened to it. So Sir C.V. Raman did what was happening with that 1% of light. That essentially tells you, now if I tell you, if you see this pictorial diagram, infrared absorption happens here, and that 1% light will either do Rayleigh scattering or Stokes lines or anti-Stokes lines, right? Now what essentially Stokes lines or anti-Stokes lines means is, Stokes is when you give energy, right, it reaches a level and then comes back but does not come back at the ground state. What happened was in FTIR was it was absorbing energy and giving it back, right? Jitna liya utna de diya. But this does not happen with the 1% of light. 1% of the light was responsible for inelastic collisions. That means jitna diya utna hi wapas nahi kiya. Essentially what it meant was, it absorbed an amount of light, went to the excited state, came back, but did not reach the ground level. It still had to keep some energy and stopped at a higher energy level, right? For anti-Stokes line, if you see, what happened was, let's assume the molecule already got some energy. So now it was not present at the ground state. It already had some X amount of energy. So now it got excited, reached a virtual excited state and came back. And when it came back, it gave up all its energy and came back to ground state. In Raman spectroscopy, we study Stokes lines, right? We studied this inelastic collision. This is normally studied if the molecule has fluorescence. Now you just have to remember this. Anti-Stokes lines are better in case of fluorescent molecules. For other molecules, for all FTIR active molecules, you use Raman-Stokes, right? So if you see the instrumentation, it is very similar. What happens, just the difference is, you have to give inelastic scattered light. That 1% of the light is given to the sample, and whatever the sample does with that light is recorded. Now, if you see the graph from it, a few molecules, like if you say OH is infrared active, so you see a very good peak at 300, 3400. But however, if you see infrared, the Raman spectra for it, it would not be active. Now, if you see CH stretch is Raman active. That means it was actually anticipating an inelastic collision rather than a elastic collision. That is why CH stretch is better in case of Raman and lesser in case of infrared. The peak would come in a very same fashion as of FTIR. The only thing that would change is you would be able to deconvolute it, in the sense you can identify different peaks. You can see 3 peaks over here, but you can distinguish them very clearly in case of Raman, right? So essentially, it's an extension of FTIR only. We are only talking about the 1% of the light that was not accountable in case of FTIR. So we do Raman spectroscopy, right? It is for the bonds only, right? Then we have optical rotation dispersion. That is when you have to analyze your sample, when you have to identify your optically active sample, if it is dextro or it is levo, right? You all know what is dextro and levo, right? So how do we identify them, or how do you characterize your sample if it is optically active? You do it with ORD, optical rotation dispersion. Now what happens is, it gives you the optical, when you say dextro and levo, it is called as right-handed or left-handed. What it means is, this instrument does this for you. What you do is, you take up light, because light travels in all the directions, so we call it as unpolarized light, right? So what you do is, you polarize your light into a single plane, right? So what we have done is, we have added a polarizer. Now the polarizer will fix your light into a single plane and discard all the other planes. So it is going straight, right? When you put your sample into your sample tube, your sample has an ability to absorb either the right-handed or the left-handed one, right? Whatever is absorbed, you can quantify, you can actually determine what amount of energy has been absorbed. So it is, your light has been bended to right direction, or your light has been bended to left direction. So essentially what it does is, how do you know it is a D glucose or an L glucose? The instrument does it for you, right? Similarly, it is for glyceraldehyde or all the molecules that are optically active. You can identify if it is dextro or levo, right? So our body, if you see, has an ability to absorb the glucose, but for everything else that is proteins, it would do it for levo. Now you have to remember this. It's a frequent question that is asked. Only dextro glucose is absorbed in our body, and rest proteins in the form of levo are normally absorbed in our body, right? The next one is circular dichorism. Circular dichorism is actually it tells you about the orientation of the proteins, in the sense it has how many alpha sheets, how many alpha helix, beta sheets, or random coils, right? Essentially what it does is, it tells you what is the composition of your proteins. When you see your proteins in bioinformatics, you see, alpha helices, right-handed, left-handed, beta sheets, parallel or anti-parallel, or random coils. So the instrument, the practical version which tells you, okay, this is alpha helix and this is right-handed. This is alpha helix, this is left-handed. That is what circular dichroism does it for you, right? So you just have to remember this. It is a circularly polarized light. The first thing that you have to remember, circular polarized light that you use rather than a plain polarized light that you did in ORD. So circular polarized light is given to the sample, and that sample will absorb according to its choice. So if it is a right-handed one, it would absorb right-handed and will give you lesser amount of right-handed in the to the detector. So what you detect is what is being absorbed. If right one is absorbed, that means your sample is right-handed. If left one is absorbed, that means it is left-handed. If you see the graph, this is the the standard graph, that alpha helix will give you peak over here, right? A beta will give you a peak and a dip, and a random coil will give you a dip only, right? So you quantify it using this, that how many alpha sheets and how many alpha helix and how many beta sheets are present, or how many random coils are present in your system, right? The last one is nuclear magnetic resonance, right? NMR. Now NMR is it has gained a popularity over the time, right? It wasn't very popular during the early start, but it has gained a lot of popularity now to understand what your molecule looks like, right? Essentially, when you wanted to know the mass, you did MS, right? Now you want to know how the molecules are connected to each other, right? How the atoms are placed in your system. Now you know the bonds also with your FTIR and Raman, right? Okay, there is a CH present, right? So to identify them or to confirm, then NMR is done to tell you how your atoms are arranged into your molecule, right? It's a non-destructive technique, and it was discovered by Bloch and Purcell, and they got a Nobel Prize for it, right? And it gives you a chemical analysis as well as molecular structure. So you get a choice. You can do FTIR in a, you and deconvolute it and then perform Raman, or you can take with MS, or you can do NMR, right? So NMR essentially is nuclear magnetic resonance. What it means is, the name only suggests, it is resonance of your nucleus, right? Now nucleus magnetic term comes because your protons, neutrons, and electrons. Protons and electrons have charge, right? And anything that has charge has a possibility of magnetization if there is an extra one, right? So what happens is, if you see if the number of protons inside your nucleus is odd, it would give you a magnetization. If it is even, it would not, right? So essentially your sample has to be NMR active in terms of odd or even number, then only you can perform it. Otherwise there is no point of it. Now what happens is, essentially, like I've told you, if it is 12C, it is not NMR active, it will not give you anything. Why? Because it has six protons and 6 neutrons, right? So it nullifies. So it will not give you any NMR signal. Now it has to be an odd number, so we use C13, N15, P31, or the best one is H1, right? So what happens is, you're doing nothing, you're just exciting your nucleus this time. So to excite your nucleus, what you do is, you give it energy, you change the orientation of your nucleus, of the spin of your nucleus, right, into one particular direction. If your sample is NMR active, it will take up this energy, the external magnetic field, right, and align it itself according to the external magnetic field. Let's assume I've put the external magnetic field and I've changed all the nucleus and forced them to go to -half, right? I've changed the spin of it. Now, as soon as I switch off the magnetic field, this will come back to its original form, that is +half, and the radio because it is in the form of radio frequency it was absorbing, it will dissipate it in the form of radio frequency only. So this -half to +half, the jumping back to the ground state will give you radio frequencies that are detected, right? So if you see the schematic representation of the instrument, you have a magnet, external magnetic field, because you have to align them with it, right? A sample, a detector, and a RF transmitter, that is radio frequency transmitter, which actually gives it radio frequencies, and then absorption spectra is recorded for it. Chemical shift is that the only thing that you have to remember in chemical shift is that you use, first thing that you have to remember is that is tetramethylsilane. This is a standard compound which will not change its position in any NMR. So this is the standard for it. It is one of the questions that are frequently asked in your paper, that what is the standard that is used for NMR, that is TMS. You have to remember this, right? Now, chemical shifting, what happens is when your molecule is arranged into according to bonds, a lot of times what happens is your nucleus is shielded and deshielded. So your peaks can differ in terms of shielding and deshielding. If your nucleus is readily available for absorbing radio frequency, your peaks might come at lower energy. While if there are compounds present which shield your nucleus, that is, or it is very densely, electrons are flowing out of the on the orbits, and the atom is very dense, though it would shield your nucleus. So a lot of energy, extra energy would be required for it to get excited, right? So your chemical shift is with respect to the shielding and deshielding effect of your nucleus, right? Now this is the graph that comes normally, right? Like I've told you, right? So you have to, according to your B naught, the external magnetic field, you get peaks, and you deconvolute it in the sense of you understand where it is positioned, and you can use it, right? So let's take quick questions, right? And you can come up with the answers yourself and see if you know anything by now, right? So when placed in a magnetic field, all the random spins of the nuclei will either stop, reverse its direction, or align with the magnetic field, or rotate 90 degree. So essentially what I've told you is, you put the magnetic field, it would align it itself to the magnetic field, right? So I think this was the easier one, right? Then in an equation, A is equals to E into B into C, that is Beer-Lambert's law. What is E? It is absorptivity, molar absorptivity, path length, or none of these. It's molar absorptivity. Then Beer-Lambert law में only Beer's law. What Beer law states is absorbance is proportional to path length and concentration, or it is just proportional to the log of concentration, or P naught by P, or none of the above. Beer law and Lambert law, दोनों ने अलग-अलग findings किया था, and they got the different, they got proportionality to different factors, and then we combined it. So it is proportional to the log of concentration. Beer gave it, right? Then Malditov is used for, I've already told you, Maldi, naam sunte, it is just for biomolecules, right? You don't have to see anything else. It is for purely for biomolecules, right? Then dextro and levo optical isomers can be characterized by circular dichroism, mass spec, ORD, or all of these. Essentially, circular dichroism, what it does is alpha helices and beta sheets. Mass spec is mass to charge ratio, tells you the mass. ORD, dextro and levo, right? So it is ORD. Last probably is the electronic transitions possible with UV visible spectroscopy. Now you have to remember, it gives you for pi bonds. It does not have sufficient energy to give it you for sigma bond. So it is pi to pi star. Anything that has pi to pi star will jump, right? So essentially pi to pi star and n to pi star. And this was a question, previous year question, that I had mentioned. Why? Because you have read a few of them, but then you should know where it cannot be used. Like lower limits of detection by sensors is important. Which method is used for pH measurement, right? Fluorescence. So circular dichroism, you know, alpha helices and beta. Refractive index will give you the refractive index, and absorption spectroscopy normally gives you where it is getting excited, right? So either you know the answer or you know what it does not do. So that would also help you, right? That is all I had to discuss today. Thank you. I hope this was useful for you. If you have any questions, I can ask sir to give you privileges for 2 minutes. You can ask me questions.
Okay, just raise your hands. I will unmute you if you have any questions. I think no questions are there. So thank you very much, Ragini madam. It's a very informative lecture. Now, participants, we are moving towards our second lecture. Okay, and it is on the circulatory system. So our second lecture is on circulatory system. It will be delivered by Dr. Meenakshi Parmar. She is an coordinator of PGDMLT in Virani Science College, Atmiya University campus, and she has more than 15 years of experience. You can get as much knowledge as you can. I will invite Dr. Meenakshi ma'am to deliver her lecture. Just wait for a minute.
Very good afternoon to all. Am I audible to all? So today we are going to cover the circulatory system. This is a part of physiology system of our body, and majority of the physiology system we have covered in your 12th standard. But at that time, you might have covered all these topics to get good marks in the 12th standard. And now we are quite matured enough to understand the whole body system. So I think you'll be enjoying more about the circulatory system now. In this particular topic, I'm going to cover functions of circulatory system, components of circulatory system, anatomy of heart, pathway of circulation, cardiac cycle, heart rate, uh, cardiac conduction system, blood and blood vessels, and if time permits, we'll cover some of the cardiovascular disorders. Right? So let us understand the functions of circulatory system. Once again, as I told you, it's not new to you about learning about the circulatory system. So the one of the major function name itself is circulation. That is, it must be circulating something, right? So it is a transporting, or it is a circulating system, or it is a transportation system by which oxygen, nutrients, they are transported uh, from the lungs and the intestine to the all the body cells, which are requiring the oxygen and the nutrients for the proper metabolism. And the waste materials are taken back from the cells, and they are carried away from the tissues and given to the kidney. So this is actually a transportation system which is actually done with the help of circulatory system, right? And another function, it is also carrying, apart from the oxygen and the nutrients, it is also carrying some of the substances which are known as hormones, vitamins, antibodies. So you know that antibodies are important for fighting the invading microorganism. That is for giving the immunity, because these substances are also carried with the help of blood itself. So again, it is one of the major function of the circulatory system. And hormones, these are important for controlling the various body processes in terms of various metabolic functions. Another function of circulatory system is to stabilize body temperature and pH. Right? These are some of the very essential functions by which you can maintain the homeostasis of the body as a whole. So this is one of the very major function of circulatory system. So I think with this you have came to know, we have come to know that the circulatory system, which is actually consisting of your blood, heart, and the blood vessels, these are doing tremendous function throughout the life, right? Now coming to the components of the circulatory system, that is, circulatory system is made up of what, or what are the major components which are included in a circulatory system? So no doubt about it, first is your heart, because it is the important organ which is actually doing the blood purification and pumping the blood to various organs. Then the blood, the major transporting media or major transporting medium, right? And the blood vessels, which is actually the pipelines which is carrying the blood. So one by one we'll cover all the three components of the circulatory system. First, we'll talk about the heart. It is a muscular pump. Whenever we think, or when we hear about the heart, it is always synonymous to the pump, because it is pumping the blood right from the birth to the death, right, till the death. Right? This is the important function of the heart, and it is roughly the same size as your closed feet, that is about 12 centimeter long, right? And as you all know that it is situated more towards the left side rather than in the center. It has an average mass of about 250 to 300 grams. It rests on the diaphragm near the midline of the thoracic cavity. In the next figure, you could see the midline, that is which is also known as mid-sternum line, which actually divides the body into two equal halves. So actually, you could see the heart is situated starting from the first or second rib, and ultimately it is resting on the diaphragm here. It rests on the diaphragm near the midline of the thoracic cavity. It lies in the mediastinum. This is known as the region from the first rib to diaphragm, and it is suspended in the pericardial sac in the rib cage of chest on the left side. Now, what do you mean by pericardial sac? This is nothing like you could see in the next figure, you could see the bag in which the heart is kept here, right? It's like a polythene bag. It's actually not a polythene bag, it is a pericardium, which is a protective sac of a connective tissue, and it is surrounding the heart to give the utmost protection. And again, this pericardium is made up of two parts. One is fibrous pericardium. As you could see, the outermost layer which is known as a fibrous layer or fibrous pericardium. Then comes the serous pericardium, and this serous pericardium is again made up of two layers. One is known as a parietal and another is visceral. Parietal pericardium is that which is next to your fibrous layer, right? You could see here fibrous layer. Then next to the fibrous layer, you could see the parietal pericardium, and in this we could see some gap is there. This is known as a pericardial cavity. And after the pericardial cavity, you have the third layer of pericardium. This is known as a visceral pericardium, which is very much attached to your myocardium, that is your heart. Actual heart, it is surrounded by this pericardium. And in this pericardial cavity that you could see here, pericardial cavity, I could see the fluid, some kind of fluid also you could see in this figure. So this pericardial fluid which is present between the heart and the pericardium, it is for giving the protection. Then coming to the next, that is next layer, that is myocardium. Myo stands for muscle, right? This is a middle layer of the heart. Myocardium, it is made up of muscle, and these are the muscles which are very strong and thick to give rise to the pumping action. And it is composed of spontaneously contracting cardiac muscle fibers. And these cardiac muscle fibers are very much different than that of the other muscle fibers in the body, because they have to bear a lot of pressure during the pumping action of the heart, and also they are involuntary in nature. And another important feature of these cardiac muscle fiber is that they are able to they can conduct the electricity like nerves, right? Rest of the other fibers or other muscles, they do not have electricity, electricity they don't have. Only the cardiac muscle fiber has a electricity like nerves. And it is important to know, in the later slides you will come to know how this electrical conductivity carried by these muscles fibers, they are important for contraction of the heart. Now these cardiac muscle cells, as you could see in this figure, they are involuntary muscles and they are striated in nature. And you could see the long muscles, and in this you have intercalated this between the two muscles to separate it. This is how your cardiac muscle look like. And they have the tremendous function of pumping, because they are very strong in nature, so they can bear a lot of pressure. Then coming to the structures of the heart, inside structure, right? From the myocardium, you have the another layer which is known as the endocardium, that is very much inside. The innermost layer of the heart is known as the endocardium. So outer layer is known as pericardium, middle layer is known as myocardial, and the third layer, that is innermost, it is known as the endocardium. And in this you have the presence of 4 chambers. These 4 chambers are divided into 2 chambers like atrium and ventricle. There are 2 atricles which are known as upper chambers. Upper chambers are known as atrium, and they are thin walled. They are receiving blood from the veins and they send blood to the ventricles. So direction of the atrium is opening to the ventricles. That is, they have the function to provide the blood to the ventricles. So this is the atrium. You could see in this figure right atrium, upper atrium, and here the left atrium. This is also upper atrium. Then the ventricles, these are known as the lower chambers. They are thick walled. They are receiving the blood from the atria. As you could see, the direction from atrium, you can downward. When you go downward, it is opening into the ventricle. They are thick walled. They are receiving the blood from the atrium. They pump blood out through the arteries. Right here, you could see the connection. In the next figure, I think it will be more clear. In between the atrium and the ventricles, you have the presence of a septum, which is dividing the heart into 2 halves, that is right chambers, right half and the left half, right? And accordingly, we are saying that it is the right atrium and right ventricle, and left atrium and left ventricle, because there is a in between septum which is partitioning the whole heart into the equal half of right and left. This is a figure which is showing you the chambers of the heart. You could see here the right atrium here, and you will see SVC. This is known as a superior vena cava. This particular right atrium, because actually your system of the heart, system of the functioning of the heart starts from the right atrium, and right atrium is receiving the deoxygenated blood from the whole body. Now upper part of the body, they are collecting the blood with the vein which is known as a superior vena cava, and the inferior part, that is the parts or organs of the body which are inferior to the heart, that is हार्ट के नीचे के जो भी ऑर्गन्स है उसको बोलते हैं हम लोग inferior organs, and these and the blood collected from these organs which is collecting in the form of inferior vena cava. You could see the figure at the bottom of the heart. You could see IVC, that is inferior vena cava. This is a very large blood vessel vein which is collecting the deoxygenated blood from the lower parts of the body, and the superior vena cava which is collecting the blood from the upper part of the body, and they are uh, they are emptying the blood into the right atrium. Then the arrow downwards here with the blue line is showing it is going downwards to the right ventricle. So this right ventricle is receiving the deoxygenated blood from the right atrium through the right atrioventricular orifice. This white portion that you could see is a valve actually. It is known as the atrioventricular valve, or you can say the orifice. This is nothing but the opening by which the blood is getting emptied from atrium to the ventricle. And then another opening is also there. You could see here, once it is coming from the atrium to the ventricle, from the ventricle it has to go to the lungs, right? And for the in the lungs they are going for exchange of the oxygen, right? So this is once again opening into the pulmonary trunk here. This is a very very thick and the what can say the very strengthy pulmonary trunk. It is also known as a pulmonary artery, which is getting when the contraction of the ventricle takes place, the blood will go from right ventricle to the pulmonary trunk, right? And on this part, from the pulmonary trunk, the blood will go to the lungs. In the lungs is exchange of the oxygen and the carbon dioxide which is taking place, and from the lungs it is coming back in the form of the pulmonary veins, and this left atrium which is receiving the oxygenated blood from the lungs via these pulmonary veins. This is a left atrium. From the left atrium, the blood, oxygenated blood, see it is very much indicated by the red. This is what you can say pure blood, and this is blue arrow, this impure blood, that is it is having more amount of carbon dioxide, and the red blood, it is red arrow is showing that it is having more amount of oxygen. So the pulmonary vein is emptying the blood into the left atrium, which is then going into the left ventricle, and the left ventricle, it is receiving the blood from the upper atrium through the again orifice or a valve which is known as atrioventricular, and it is sending the blood to the aorta. You could see the red large blood vessel which is known as the aorta, and from the left ventricle the blood goes to the aorta for distributing the blood to the whole, the various different parts of the body, right? So this is actually the chambers of the heart, and in short I'll just show you the circulation. Then as I told you that there are certain opening and closing of some orifices, or the holes are there, openings are there. So I'll just let you know these are known as the valves, right? So these are the valves. As we know that valve has a important function of preventing the flow of the blood, right? So valves has a function of preventing the backflow of the blood. So it is they will keep the blood moving in only one direction. You can just imagine if the valves are not present, right? What will happen? Once the blood is coming from the atrium to ventricle, and ventricle when contracts again, the blood will go to the aorta, right? So this should not happen. It should be going to the pulmonary vein only, pulmonary artery only. So that's why you have been given a special valves which opens in only one direction. It cannot go back to the atrium, right? So these are the valves, and there are two types of valves. One is aortic. They are not atrioventricular valve, that is between the chambers, right? Atrium to ventricle, there are left chamber and left and right. On both the both the side, you have a valve which are known as the atrioventricular valve. On the right side, you are having a tricuspid valve, and on the left side, you are having a bicuspid valve. Bicuspid valve is also known as mitral valve. This figure is showing actually you can say the transverse section of the heart, where you could see the cusp, or you can say the valves. This is right atrium. You could see the tricuspid valve. Tricusp is like a lip-like opening, right? Cusp is not particularly, it is like a lip portion. In the very next figure, I'll just show you how the valves are opening and closing. And this is the mitral valve between the left atrium and the left ventricle. And aortic valve, that is from left ventricle to the aorta, this is known as the aortic valve. And from the right atrium, right ventricle to the pulmonary arch, it is known as a pulmonary valve, right? So these are the four different valves which are present, and they are having the opening and closing according to the contraction of the heart. Okay, as I told you, how the cusps will look like, right? When the how the opening and closing of the valves which are taking place. You could see the strings-like structure here, right? These are the strings-like structure which are known as chordae tendineae, right? Chordae tendineae, they are important for making the valves open and close, right? And you could see the cusp here, right? This valve is a bicuspid valve. This is a figure of bicuspid valve, and these chordae tendineae, they are connected to the papillary muscles, and these papillary muscles are responsible for contracting this chordae tendineae. It is making the chordae tendineae to stretch the cusp so that the valves get open and close. So chordae tendineae, they are also known as heart strings. They are cord-like tendons, and they are connecting to the papillary muscles, to the tricuspid and the mitral valves, and they are preventing the inversion of the valve. Right? These are the figure which is showing you the white strings-like structure, and they are connected to the papillary muscles. Right? So papillary muscles, when the contraction is to be done, then at that time this papillary valve, they will make the tricuspid valve to be closed, so that another valve, that is pulmonary valve, should open and the blood should go up and not go back to the atrium. So in a way, the heart, the lungs, and the blood vessels, heart, lungs, and the blood vessels, they work together to form a circle, and that's why it is known as a circulatory system. So now let us understand in short about the circulation, as the name circulatory system. So heart acts as a double pump, right? Because it is having a left part and the right part. So it is acting as a double pump. It is a two separate pumps. Blood from the right side of the pump is dark red and low in oxygen. That is known as oxygen poor, because they are collecting the blood from the all parts of the body. They are the deoxygenated blood. That's why they are flowing into the veins. That's why they are coming from the veins, superior vena cava and the inferior vena cava, and they are emptying the blood into the right atrium. They travel to the pulmonary arteries to the lungs, where it gets fresh oxygen and becomes bright red. And the blood from the lungs through the pulmonary veins back to the heart's left side pump, and this is pumped out into the body. Right. So this is the circulation of the system. Right. So I'll just show you oxygen poor blood, right? Oxygen poor blood draining from the body through the veins into the superior and inferior vena cava flows to the right atrium. You could see the blue part. This blue part is actually your deoxygenated blood. This is known as a inferior vena cava and superior vena cava, and they're collecting the blood from whole parts of the body and emptying into the heart. And as the right ventricle contracts, oxygen poor blood passes through the pulmonary valve into the pulmonary artery and onto the lungs to receive the oxygen, right? So the blood is coming from the whole body parts to the lungs, to the heart. From the heart, the blood is going to the lungs, right? In the lungs, it is getting exchanged, and from the lungs, you have the fresh blood, okay, say the pure blood is coming back to the heart, and from the heart, it is going to the aorta, and from the aorta, it is going to the whole parts of the body. So, this is oxygen poor blood, which is coming from the various part to the right side, and this is oxygen rich blood, right? This is the same figure, but I'm just showing you the pathway of the pure blood, right? Oxygen rich blood from the lungs enter the heart through the pulmonary veins, passing into the left atrium, then through the mitral valve to the left ventricle, contraction of the left ventricle, which is forcing the blood through the aortic valve into the aorta, and various arteries branch off from the aorta to supply the blood to all parts of the body. So this is actually the major circulation of the blood through the various organs. So there are three kinds of circulation. Pulmonary circulation. If one asks what are the different kinds of circulation, there are three kinds of circulation. One is pulmonary circulation, second is coronary circulation, and third one is systemic circulation, right? One by one we'll take it in terms of figure only. This is almost type of a revision, but under the different headings you should know about the kinds of circulation. The pulmonary circulation, that is movement of blood from the heart to the lungs and back to the heart again, right? There already I have told you that from the right ventricle, which is having a deoxygenated blood, it is going through the pulmonary vein, right? This is a pulmonary artery. Now, everyone knows that arteries are the blood vessels which are carrying the pure blood, that is oxygenated blood, and veins should carry always a deoxygenated blood. But here is an exception, right? Always you should remember, always pulmonary vein is carrying the pure blood and pulmonary artery is carrying the impure blood, right? So you could see here the blue part is showing your pulmonary artery, right? Pulmonary trunk is divided into two parts, that is left pulmonary artery which is entering into the left lung, and it is branching here to give rise to the right pulmonary artery which is entering into the right lung, where the exchange of the gases which is taking place. The poor blood, oxygen poor blood, has a more amount of carbon dioxide which is exchanged with the oxygen, and they are collected in the form of pulmonary vein. You could see here, right? Left lungs has an entry of blood by artery, but it is leaving the good blood or pure blood in forms of vein, pulmonary vein. And this pulmonary vein, they from both the lungs, they will enter into the left atrium. So this is a pulmonary circulation. Then comes the coronary circulation, right? Coronary circulation is movement of blood through the tissues of the heart. You could see the back part, or you can see the aorta, right? I think we know that from the left ventricle, the blood is coming out of the heart for distribution of blood to the various parts of the body, and that region is known as blood vessel is known as the aorta. And this aorta, you could see here, which is a very, very large, highest diameter of the blood vessel is that of aorta. And aorta is, again, they are branched. You could see the branches here, right? And this aorta is branched here to give rise to coronary artery, right? These are the coronary artery. This is known as a coronary circulation. If the heart is doing such a tremendous function, it should also getting the nutrients, right? It is also should be getting the nutrients, right? So how the heart is getting nutrients and the oxygen? So it is through coronary artery, right? So once the good blood or the pure blood is coming out in the form of aorta, aorta first branch is into the artery, in the coronary artery, and this coronary artery again they branches and rebranches like left and the right coronary branches, coronary artery branches taking place, and you could see the network of this coronary artery, and this is providing the blood and oxygen and nutrients to the heart for the major function. So this is known as a coronary circulation. And the systemic circulation, we already know that supplies nourishment to all the tissue located throughout the body with the help of the aorta, right? Aorta is once again branch and rebranch, and it reaches to every part of the body. So this is a circulatory system. Now coming to the very important part or concept of this circulatory system, which is also known as the heart of the heart, right? It is a cardiac conduction system. That is how the pumping mechanism is done so tremendously and so meticulously throughout the life, so that each and every organ, each and every cell tissue are getting enough amount of oxygen, right? How the heart is doing such a tremendous work, and that is with the help of your cardiac conduction system. So why heart beats lifelong? You might have a question, right? We always know that heart beats continuously. Once the heartbeat stops, our life also stops, right? So how this heartbeats is carrying out important function, and it is known as a cardiac cycle also. So heartbeat is why the heartbeat should always taking place due to the inherent and rhythmic electrical activity, right? How the heartbeat takes place? It is because of inherent and rhythmic electrical activity, and this inherent rhythmically electrical activity is because of cardiac muscle fibers, right? Previously I told you that myocardium is made up of the muscle fibers, and these muscle fibers are autorhythmic fibers, right? That is, they are able to do self excitation. These fibers are known as self excitable, right? They can generate the accent potentials by themselves, right? There is no other trigger. So they repeatedly generate the accent potentials that triggers the heart contraction. How the heart should get the message that I have to contract, right? So this message is given by the electrical potential which is generated by the heart muscle itself. They continue to stimulate heart to beat even after it is removed from the body, right? So this is such a what you can say that sometimes you must have seen also after the, that's why the what you can say that transplantation of the heart is possible, because even if it is coming out of the body, it beats for some time, because the after it is disconnected from the whole body, but muscles are still, they are producing the action potential, so they can keep the heart beating, right? So autorhythmic fibers have the two functions. Now let us understand about how these autorhythmic fibers works. So there are two major functions of autorhythmic fibers. One is it is acting as a pacemaker that sets the rhythm of the electrical excitation. Right? Pacemaker is nothing but it is making the rhythm of the electrical excitation. And another, they form the cardiac conduction system that provide path for each cycle of excitation to progress through the heart. Right? The electricity that is generated into the heart, it should be traveled through whole parts of the heart so that the contraction takes place. Then and then only the whole chambers of the heart becomes active, right? So the conduction system ensures that cardiac chambers become stimulated to contract in a coordinated manner. Thus heart behaves as an effective pump, right? Coordinated manner में काम करना बहुत जरूर है, right? If atrium says that I will not contract at the same time, then what will happen, right? So you can imagine such a coordinated system of the chambers is taking place, so that when the atrium is contracting, the ventricles are relaxing, and when ventricles are contracting, the atriums are relaxed, right? So this is, you can show that the coordinated manner of the heart pump, right? So here it is a cardiac conduction system. What it is made up of? One is known as SA node, that is sinoatrial node. Another is AV node, atrioventricular node, bundle of His, Purkinje fiber. These are the four components of cardiac conduction system. This sinoatrial node that you could see here, it is located high at the right atrium. It is actually the fibers only, right? Here it is shown as a very small button. Is shown as a button. It is actually made up of the fibers only, muscle fibers, and they are self-excitable. So the generation of the action potential or electricity starts from the sinoatrial node, so that the right atrium, both the atrium, they are getting the electricity, so that they get stimulated to go for contraction, and this stimulation is carried forward to the AV node, right? Sinoatrial node is made up of muscles. The once the electricity has started from this node, it is carrying this electricity to the next node, that is known as a AV node, which is nearby the atrioventricular. It is near to the valve, right? Atrioventricular valve के बिल्कुल नजदीक में atrioventricular node is there. From the atrioventricular node, the further electricity is distributed to the bundle of His. You could see in the septum. This is bundle of His, and then again it is this bundle of His. It is divided into the two branches. One is known as the left bundle branch, and another is known as the right bundle branch. And these bundle branch are known as the Purkinje fibers. Name of the scientist, Purkinje fibers. So very shortly, I'll just tell you, sinoatrial node, it is located high on the right atrium. It is a pacemaker of the heart, right? One can ask, what is who is a pacemaker of the heart? It is a sinoatrial node. It is generating the action potential and sends to the AV node, and it is causing the wave of contraction in both the atrium, right? Once the electric action potential is generated in the SA node, both the atrium, right and the left, they both contracts, and the blood is emptied into the ventricle. At AV node, the action potential slows down due to the difference in the cell structure in the AV node, right? When the electric conduction or electricity comes to the AV node, it slows down little bit, right? And then this delay provides the time for atria to empty their blood into the ventricle, right? So this is the time where the atrium, after the contraction of the atrium, the blood will come to the ventricles, that is at the lower chamber. Then the atrioventricular node, this is known as the AV node, which is located in the interatrial septum close to the tricuspid valve. It is carrying the electrical pulse into the bundle of His, right and left bundle branches, and finally the Purkinje fibers through interventricular septum, right? They are all found, they are present in the septum, and this causing the ventricles to contract. This particular small, what can say, the figure shows very slowly how the electricity is passing from SA node to AV node to bundle of His, and then to it is going back, it's going to the Purkinje fibers. Very slowly, one by one, it is going. Here it is showing very slowly, but actually whole of the SA node to the Purkinje fiber just take 0.8 seconds. Right? The location of nerve fibers bundle, nerve fiber bundles cause the ventricles to contract from the apex, that is from the bottom. So the blood will be contracted and is coming. It will squeeze the blood up and out. Autorhythmic fibers in the SA node initiate an action potential about every 0.6 seconds, right? Autorhythmic fibers, I'm reading once again, fibers in the SA node initiate an action potential every 0.6 seconds or 100 times per minute. And nerve impulses from the autonomous nervous system and hormones like epinephrine, they modified the timing and strength of each heartbeat, but they don't establish the fundamental rhythm. Fundamental rhythm is to be set by SA node itself. Only thing, according to the hormones like system, you might have the heartbeat goes very high. Otherwise, normal heartbeat, that is 72 beats per minute. This is almost, this rhythm is set by the SA node itself, right? Now coming to the electrocardiogram, this is we have seen many times, right? An electrocardiogram is also known as EKG or ECG. It is a composite record of action potentials of electrical signals which are produced by heart during each heartbeat of one cardiac cycle. So we'll learn about what do you mean by heartbeat or a cardiac cycle. Now, during the action potential, you have the generation of the P wave starting from the SA node, right? Whenever the electricity starts or begins at the SA node, you have a P wave, that is contraction of the atrium. This is known as a atrial depolarization. You could see the figure here, PQRST, right? This is how the waves are shown here. This is in milliseconds, right? You can imagine such a organized manner this your conductor system is working, and very coordinately it is contracting and relaxing the heart muscle, heart chambers. Then the QRS complex, it is onset or beginning of the ventricular depolarization, and T wave, QRS is a beginning of your ventricular depolarization. Depolarization is nothing but contraction, and T wave is a ventricular relaxation. When the blood is emptied from the ventricles, it is known as a ventricular repolarization, right? And this is in a very systematic manner how the SA node and generates the P wave, and the AV node generates the QRS wave, and the QRS wave is actually depolarization of the ventricles, which is up which is starting from the bottom and causing the QRS complex here, and the atrial repolarization takes place, right? You could see the yellow part, that is your depolarization, that is contraction, and the red part, that is your relaxation, or you can say the repolarization, right? So this figure shows PQRST waves are generated one by one. Accordingly, your cardiac or action potential goes from SA node to the Purkinje fiber, right? This is also a similar figure. So now, what is cardiac cycle, right? Now you are able to know very clearly what you mean by cardiac cycle. That is, it is a type of a heartbeat, right? It is refers to all the events from beginning of one heartbeat to the beginning of the next heartbeat. It is known as a cardiac cycle, right? One beat, that is your PQRST, right? This is one beat, PQRST. This is your one beat, right? One beat to another beat, all these events is known as your cardiac cycle. When cardiac muscle contracts, it does so as a single unit, creating a heartbeat. And one heartbeat or a cardiac cycle is consisting of two parts, which is known as a systole and diastole. Again, new terms have come, right? One term you know very much clear, contraction and relaxation. These are very ordinary terms, everyone knows about it. But medically, it is known as a depolarization and polarization. Depolarization is known as a contraction, and repolarization is known as a relaxation. Again, new terminology in terms of your heart cycle, or you can say cardiac cycle, systole and diastole. Systole is your contraction or depolarization, and diastole is your relaxation, right? So these three terminologies interchangeably you are able to understand, you can use it. Systole, that is your heart muscle contracts, and diastole when heart muscle relax, right? So cardiac cycle, the term systole is synonymous with the contraction of the muscle, and atrial systole is the contraction of the heart muscle of the left and right atrium. It lasts for just 0.1 second. Just 0.1 second. You can imagine it's just a millisecond, right? Atrial systole is a contraction of heart muscle of both the atrium. It is just lasting for 0.1 second, and depolarization of SA node causes atrium depolarization marked by P wave. The P wave is with the help of your SA node, starting with the SA node, and depolarization of the atrium. It is making the P wave. both the atria contract at the same time, which is sending the blood to the corresponding ventricles. And when the ventricular systole, that is contraction of the ventricles, it is a contraction of the muscles of the left and right ventricles which contract at the same time, and they are generating the QRS wave, right? QRS wave is generated by ventricular systole and it lasts for 0.3 seconds, right? So atrial systole and ventricular systole together they last for 0.4 seconds. Then coming to the diastole. Diastole is a period of time when the heart relaxes after contraction, right? Diastole is a period of time when the heart relaxes, that is after contraction. It is lasting for 0.4 seconds. And oxygenated blood from the lungs, they fills the left atrium, and the deoxygenated blood from the other parts of the body fills the right atrium. And at the end of the diastole, atria contract, starting the systole. These are, you can say, one by one, the system goes on. It's not that ki diastole आराम से हो गया, उसके बाद atrium starts. It's all simultaneously. It is taking place so fast, and that's why heart keeps on beating. This is the heart sounds. Two normal heart sounds with each heartbeat. It is described as two words, lub and dub. We say dhak dhak. Actually, it is a lub and dub. Lub is known as a sound due to the closure of atrioventricular valve. Atrioventricular valve, that is mitral and the tricuspid valve, that is between the atrium and the ventricle. For when these valves are closing, at that time the lub sound comes. And when the aortic and the pulmonary valves closes, at that time dub sound is found, right? So this is a lub and dub sound during the cardiac cycle. Then coming to the heart rate, that is count of each heartbeat. On an average, a heart beats 72 times a minute when it rests, and it is usually calculated as number of contraction of the heart in 1 minute, and it is expressed as BPM, that is beats per minute. The pulse is the most straightforward way of measuring the heart rate, and it is controlled by the nervous system. You have a sympathetic nerves and the parasympathetic nerves. Norepinephrine and the epinephrine, these are the enzymes, hormones, which are important for increasing the heart rate. Also, some of the exercises when you have a high body temperature, when you need for oxygen and food, when you are under stress, when you are excited, at all this time, your heart rate increases. And when you have excess potassium ions, when your acetyl-CoA increases, at that time your heart rate decreases. This is how your regulation of heartbeat takes place, or heart cycle takes place. Cardiac output, this is to be calculated with the help of the heart rate and the stroke volume, right? So what do you mean by cardiac output? This is the amount of blood pumped by each side of the heart in 1 minute. How much amount of blood is pumped out of the heart in 1 minute, which is known as a cardiac output, which is calculated by this formula, heart rate multiplied by stroke volume. Heart rate, everyone knows that it is a beats per minute. It is known as a heart rate. And the stroke volume is volume of blood pumped by each ventricle in one contraction. That is, in one contraction, how much amount of blood is pumped by the ventricle. And on an average, it is about 70 ml per beat. In each beat, 70 ml of blood is pumping out from the ventricle. So on an average, you have, if you calculate 75 beats per minute as your normal heart rate, and 70 ml is your stroke volume. So on an average, you have your 5000 ml of cardiac output per minute. So you can say that per minute, you have almost 5 liters of blood which is coming out of the blood after the purification. Then coming to the blood pressure, we already know the word systolic and the diastolic. So systolic blood pressure, when the ventricles are contracting, this is known as a systolic blood pressure. And the diastolic blood pressure, that is when the ventricles are relaxing, and this is known as a diastolic blood pressure. So this is the blood pressure which is generated on the ventricles, right? So this is the systolic and the diastolic blood pressure, and how much amount of the blood volume is there, accordingly your BP changes. On an average, your normal blood pressure in the adult is 120 systole and 80 diastole. It is written like this: 120 millimeters of mercury and 80 millimeters of mercury, right? Now, this is another system which is responsible for the regulation of the blood pressure, which is renin, angiotensin, aldosterone system. Is also known as a RAS system. Renin is actually released by the kidney when the blood volume falls or the blood flow decreases, and this is this renin. I'll just show you in the terms of figure so it becomes more clear. So whenever you are suffering, you are having a dehydration or sodium deficiency or hemorrhage, or these are some of the reasons why your the blood volume decreases, then it is stimulating your kidney to produce renin, and this renin is converted, this renin will convert angiotensinogen into the angiotensin, and this angiotensin 1 is converted into the angiotensin 2 with the help of enzyme which is known as ACE, that is angiotensin converting enzyme. So you can see the liver, kidney and your lungs, all they are coordinatingly, right? They are having a good coordination. Whenever you have your blood volume, it goes low, right? All these three coordinatingly, they are making the system to increase the blood pressure. So renin from kidney, then angiotensinogen will getting converted into angiotensin 1 with the help of renin. Then angiotensin 1 is converted into angiotensin 2, and this angiotensin 2 has effect on the adrenal cortex to produce more amount of aldosterone hormone, and this aldosterone hormone which is increasing the sodium and water reabsorption, and ultimately it is increasing the blood volume, right? On the other way, this angiotensin 2 is also having effect on the blood vessels. So the blood vessels of the artery, the blood vessels, these arteries, they are getting contracted. So ultimately, they are increasing the blood pressure. So from the stimulation of your low blood volume, your aldosterone is working very hard to increase the blood volume. So this is how your blood pressure is regulated. Another way by which you can have the regulation of the blood pressure is by epinephrine and the norepinephrine. These are the hormones which are produced by adrenal medulla in response to the sympathetic stimulation, and they increase the cardiac output by increase the rate and force of heart contraction. And antidiuretic hormone, that is ADH or vasopressin, which is which is produced by the hypothalamus, which is released by the posterior pituitary. In response to your dehydration or decreased blood volume, they are increased, and they will cause the vasoconstriction, as well as they will also causing the water reabsorption, which is maintaining the blood pressure. And the third hormone, which is known as atrial natriuretic peptide, ANP, atrial natriuretic peptide. This is released by the cells of atria, that is your heart. They lowers the blood pressure by causing the vasodilation and promoting the loss of salt and water in the urine, and they reduce the blood volume. So all these hormones, they are actually regulating the blood pressure by either increasing the blood volume or by decreasing the blood volume. So this is all about the heart. Then coming to the next component of the circulatory system, that is your blood vessel. These blood vessels, they are of three types: arteries, veins and capillaries. Everyone now knows that arteries are the vessels which are carrying the oxygenated blood. Veins are the blood vessels which are carrying the deoxygenated blood, and capillaries are the vein where there is a mixture of the oxygenated and the deoxygenated blood which is taking place. These are the major functions of the blood vessels, and by anatomically there is a difference between the artery and the vein and the capillary. Here you could see the arteries are very strong because they have to carrying the oxygenated blood, right, which is pumped from the heart, and it has to reach to the various parts of the body, various cells of the body. So it is having a tunica and media which is very thick, muscular, and you have a diameter of the arteries, internal diameter of the arteries is also very little bit small, so that the pressure is generated. And in case of veins, the arteries, so in the veins, the lumen is diameter is slightly more, and you also have a presence of the valves here, which is not the case in case of capillary or either in the artery. And these valves are responsible for the preventing the backflow of the blood. And these arteries, so these capillaries are very thin, and they are responsible for site of exchange of the nutrients and the gas, and they are most permeable, right? It is reaching to each and every part of the tissue. Now coming to the blood, there is a third component of the circulatory system, that is your blood. It is a circulating connective tissue, right? Usually we say that connective tissue is a solid, but only the blood is a connective tissue which is a liquid form, right? It is a circulating connective tissue which is consisting of several types of cells suspended in fluid medium, which is known as a plasma, right? And the cells are RBCs, WBCs, and the platelets. And all these different cells have a various functions, and they travel through thousands of miles of the blood vessels, and they carry nutrients, water, oxygen, waste products to and from the body. So the functions of the heart, circulatory system is the function of the blood vessels, right? Red blood cells, individually, if you can say that different cells have different functions, like RBCs, they are carrying the oxygen, and they give the blood to, they are exchanging the oxygen and carbon dioxide to the various cells. And white blood cells, they are protecting the body from the various microorganisms. They destroy the various pathogenic organisms which enter from their body. So it is actually protection, giving the protective function to the body. And platelets, they are the blood cells. They are helping the hemostasis, that is stopping of the bleeding. So these are the major functions of the different cells. So in a nutshell, when you see the functions of the blood, it is also having a messenger function, because it is including the transport of hormones and signaling of the tissues. These are some of the other functions. Then the coagulation, self-repair mechanism, then regulation of body temperature, regulation of body pH and iron concentration. These are some of the other functions of the blood. Now, as I told you, some of the circulatory system disorders, I have a little time, so I'll just touch upon the circulatory system disorders. Heart disease, in general, they are known as. Various risk factors are very common in almost all heart diseases. These are older age, male gender, smoking, high cholesterol, diabetes, stress, obesity, heredity, physical inactivity, and high blood pressure. These are very, very common and general risk factors for almost all heart diseases. So one by one, I'll just take in few minutes about the atherosclerosis. It is nothing but your formation of your atheroma, or formation of the plaque, which is made up of bad cholesterol, that's LDL cholesterol, which is actually deposited into the coronary artery, and it is damaging the inner layer of the artery, and ultimately they will block the artery, make the arteries more less flexible, increases the blood pressure, and ultimately the heart attack can take place. So this is the atherosclerosis. As you could see, this is a normal artery, and as in how your cholesterol getting increasing in blood, and they deposit into the inner part of the artery, and ultimately the yellow part that you could see is a plaque formation. They will narrow the diameter of the artery, so that the blood will not reach to the heart. As much amount of blood should reach, so ultimately the heart attack or heart failure could take place. Hypertension, this is the high blood pressure. This is making the heart and blood vessels work harder, and increases chance of heart disease and heart attack or a stroke. Heart attack is actually also known as acute myocardial infarction. This is actually not disease, but you can say the output of the atherosclerosis. because of the coronary blockages, and it is causing the death of the heart muscles and causing the death of the person also, right? And this little animation, you could see the arteries getting blocked here, and ultimately you are having the damage to the heart muscles or death of the heart muscles. These are some of the very common symptoms of the heart attack. When you see chest pain and squeezing or heavy pressure on the chest, then shortness of breath, nausea, vomiting, then pain which is radiating from the shoulder to the arm, and these are some of the very common symptoms of the heart attack. Thrombosis or embolism, these are the formation of the clot or thrombus into the blood vessel that will obstruct the way of the blood, and it will cause the nutrient supply. It will block the nutrient supply to the various organs where the thrombosis is taking place. In embolism, when this clot moves from one area to the other area through the circulation, and wherever it goes, supposing it has reached to the kidney level, kidney region, then it will block the blood supply to the kidney and so on. So this is known as embolism. This is a valve disorder. Some of the valves which are not being able to, they are not stout enough, so they will not open and close properly. So these are some of the valve disorders. I'm not going in much detail because of scarcity of time. Heart murmur, this is a whooshing sound between the heartbeats. These are sometimes because of the valves, right? Again, this is because of the valve problem, and sometimes even children are having the murmur. This is very common. You could see the whooshing sound when the child is sleeping or when he's breathing. You have a whooshing sound. This is known as a heart murmurs, right? Aneurysm, this is the blood filled dilation of the blood vessel which is caused by disease or weakening of the blood vessel and causing the poor supply of the blood. So in nutshell, I have covered the heart as a pumping mechanism to supply the good amount of blood in terms of this taking the deoxygenated blood and carrying the supplying the oxygenated blood to all parts of the body, right? And this is the cardiac cycle I talked about, and the heart rate also talked about, and some of the regulatory mechanisms of this heart cycle. So thank you very much. If you have any questions, you may ask. I'm happy to take one or
Thank you very much, madam, for your very knowledgeable lecture. So, participants, if you have any question, just one or two, you can ask. I will unmute you. Or you can also send your questions to the WhatsApp group. I will forward it to the madam and she will give you the answer. Okay. So we are running short of time. So quickly, we have a break of around a half an hour, and we will continue the session at 4:30. Okay. So please don't leave. Just be sign in, and we will be back at 4:30. Okay. Thank you. Hello. So participants, we are back. Now our next, in the continuation, we have a next lecture on plant embryogeny. It will be delivered by Dr. Mayur Parmar sir. He is an assistant professor in biochemistry department in Virani Science College in Atmiya University campus. Okay, and he is a net qualified, gate qualified, and he has already uh, qualified many competitive exams, and he will definitely guide you in completing and competing for the different examinations. So I will welcome Mayur Parmar sir. Just a minute.
हाँ अब यहाँ से okay. Hello, good afternoon, everyone. Am I audible? Anyone can reply me. Yes, I'm audible. Thank you, guys. I'm Dr. Mayur Parmar, working as assistant professor in biochemistry department in Virani Science College. Uh, Before we start about plant embryogeny, I would like to mention few of the aspects, and these are related to the particularly discipline of this class, because my lecture will be a kind of interactive session. So I would like you to interact with me. Majority of the question will be asked from my side, and you will try to give the answer. And those who want to give answer, please raise your hand, and then you can answer accordingly. Don't just mess up with all the things. Okay, before we start embryogeny, I would like to ask you certain questions. These questions are related with the terminologies, because in plant embryology, majority of the problems are associated with the terms. Most of students don't able to understand actually what is the meaning of all these kind of terms, and frequently you must be clear with this particular type of terms. So to check, to verify what do you mean by all these, I will like to ask you some question. So first question is this one: pollen grains and male gametes are same or different? Those who want to answer, please raise your hand, and then you can unmute and you can give the answer. ठीक है? क्वेश्चन क्या है? अगर pollen grain और male gamete वो सेम है या डिफरेंट है? You simply have to answer the question with appropriate reason. Anyone from your side? Or otherwise, I will randomly pick up any of the student and he or she has to give the answer. If you don't know, you just tell me that I don't know, or there kind of confusion. Anyone? Is there any difference in pollen grain in male gametes? Are they same or different? Anyone? Okay, Megaruparelia. Can you give the answer? Do you have any thoughts regarding it? Mega, please, you have to give the answer. Otherwise, anyone apart from Mega, Nandini Vasa, then Nikita, Chandil Nikita. Anyone can answer out of these three. Because this is the major concern. Majority of students actually confuse what is the pollen grain in male gamete. Are they same or different? Because such kind of question never asked by anyone. I will ask. Bolo bolo, Nikita. All of them. Fancy, Fanny. Okay, another question. If you don't know the answer, I will make it clear. What is the relationship between ovule and seed? You have to identify what kind of relationship between ovule and seed. How they different or part of something like that. If you don't ever heard ovule, that is also fine. Another question is the most important question. Apart from this is a kind of technical term. Ovule as well as male gamete, greens, no problem with that. But if anyone asks you what is the importance of fruits in context with plants, what is your answer? Why plant produce fruits? Are fruits for themselves, or you can say for plants, or they're for us? Anyone? Nobody is actually clear or any kind of issue with that. Goti Janvi, Hiral.
Participants, you can unmute yourself and you can answer.
Anyone? How many? Total 47 participants are there, and I think so. Let's move on. I don't think so. This would be a kind of interactive session, maybe. So I just will throw the information, and you have to grasp it. So still, you have to answer few of the questions, which I will definitely ask during my presentation. So please try to concentrate on the concepts, and within the meantime, you can find answer related to the difference between grain as well as pollen grain particularly and male gametes. What is the relationship between ovule as well as seed? Certain other terms are also there. One is pollination. We all know very well that pollination is a very common thing, and the majority of individuals are quite very clear regarding pollination. Then these terms are quite bit complicated. Microspore, megaspore, then one is sporophyte, another is gametophyte, male and female gamete. Most of students feel that they are a bit kind of confused, or you can say confusing things are there associated with this. But I would like to make you clear about this particular term, that is sporophyte. When you hear phytic structure, that indicates it is bearing structure, it contains it, वो अपने पास उस चीज को रखता है, ऐसा आपको समझना है उसको. So what is the meaning of sporophyte? So sporophyte is the structure which possess, or you can say which produce spore, sporophyte. Likewise, if you say gametophyte, what that means? They are gamete producing structures. So these two terms should be clear. One is sporophytic structure, another is gametophytic structure. The sporophytic structure will produce spore, gametophytic structure will produce gamete. Now, what about this microspore and megaspore? Anyone? What is microspore? Any another common name which you can say about microspore? Microspore is also called as. Such kind of questions can be asked in competitive examinations. Microspore, pollen grain, male gametes. Are they same or different or any kind of connections with them? If you think of anyone, then I have to make it clear. Microspore, micro is a smaller structure, and spore, we know that the spores are there in the microbiology. Even in the bacterial cells we can observe spores of the bacterial cell. What these spores are, they are resistive structures. The same way in the plants, resistive structures are spores, and if they are smaller in size, then it is microspore. So why they are smaller in size, and what is the concern related to the smaller size? We know in general reproductive system also, male gametes particularly are smaller in size and female gametes are larger in size. We generally call them sperm as well as egg. So there is clear cut difference exists between size of the male gametes and female gametes. So same kind of thing you can also experience over here. Microspores are the spores which are male in nature in that sense. And they are nothing but they are pollen grains. So pollen grains are also called as microspores. So megaspore would be, obviously it would be opposite. They are the spores which are considered to be female spores. So microspore is the another name which we commonly called as pollen grain, and they are totally different from male gametes. So mind well, never say pollen grains are male gametes. Male gametes in plants are totally different. They are produced by the pollen grains, and how they produce and on basis of that we'll discuss in later on stages. So pollination is the process of transfer of pollen from one flower or that kind of stuff. You already know that. I'm not going into the detail of that. Microspore are nothing but they are pollen grains. They are smaller in size compared to the female spore. Female spores are called as megaspore. So what are sporophyte? Sporophytes are the structure which produce spores. Gametophytes are the structure responsible for the production of gametes. You have to be clear with that. Male and female gametes are also the term which you need to understand. About pollination, certain agents are there. So these kind of questions can be asked. What type of pollinating agents are responsible, and based on that pollinating agents a certain type of phyli is given. Insect is entomophily, birds is for ornithophily. That means pollination is governed by birds, then that kind of pollination is called as ornithophily. A sense ma, you have to understand this. So in the pollination, certain agents are abiotic like wind as well as water, and biotic factors are also there. They include certain animals. They, in general, called as zoophily, and include insect, birds, bats, snails, and snakes likewise. So this is for your data. You can remember and you can recall it during the course of examination. Okay. Now this is the point which I would like to introduce. That is development and the structure of male gametophyte. Now anyone has to give me the answer about this, because when you read development and structure of male gametophyte, you will be confused what I have to explain, what I have to understand from this title, that is male gametophyte development. Anyone, what would be there in the male gametophyte structure? What that indicates? Okay, it will contain male gamete. It will contain male gamete, as we know that it is phytic structure, and starting is male gamete. So male gamete containing structure will be male gametophyte, and we will try to discuss the structure and development. I repeat, structure and development. So this would be totally different, and it's a large topic which includes anther, then component of anther, structure of pollen grain, and then once you understand pollen grain structure, then we will understand the male gametophyte structure, how it develops. So first of all, our understanding would be lies with respect to the development of pollen grain. Once we understand the structure of pollen grain, then we will shift to the development of male gametophyte. So starting with the structure of anther. So this is the cross section and everything. Most of things are concerned with the anther. Anything which you understand is in the structure of anther. This is the cross section. We can observe in the anther the specialized tissues in which pollen grains are being produced. The four areas we can observe, they are called as pollen sac. Within the pollen sac, you can observe different types of tissues, particularly tissues which are responsible for the spore formation. And now we know that spore is pollen grain. And what is the name of that spore? Another name, microspore. So sporogenous tissue, what that term indicates? Sporogenous tissue, spore producing tissue, or the tissues from where synthesis of spore happens. So that sporogenous tissues are lying over here, there at the center, in ore fall locules, or you can see in the pollen sac. So in the pollen sac, we can observe the presence of sporogenous tissues. What would be the ploidy of sporogenous tissues? What do you say? Anyone? Ploidy of the sporogenous tissue. Because so many questions are continuously flooding in my mind, but I am not able to ask you because the majority of the students are not at least replying. You just have to try it out, because based on your question and based on your understanding, uh, uh, we will proceed further. Otherwise, what happens? Majority of the things you know very well, I will discuss them, and you will not be benefited. So if you don't know certain things, then that particular topic should be discussed in detail, or kind of a doubt solution can happen. Anyone? What is the ploidy of sporogenous tissue? And what is the difference between pollen mother cell and pollen sporogenous tissue? We know that PMC, that is pollen mother cell. Anyone can tell the difference between sporogenous tissue and pollen mother cell? Are they same or different? सब सो गए लगते हैं चाय पानी पीने के बाद. Okay, I'm back. Anyone please? Otherwise, this kind of thing will be something like this only. You please try to raise your hand so we can unmute you. So that can happen. That can be much more appreciated. Okay. If there are no answer, then I have to explain it very clearly. Sporogenous tissues and pollen mother cells are different. Sporogenous tissues are the cells, you can understand that. Sporogenous tissues can become pollen mother cells, or they are, when they metabolically active, and they want to do cell division. Once they cross G1 S G2 phase and now ready to divide, so that enlarge, or you can say potential to divide cells, are now considered as pollen mother cells. So you can understand that sporogenous tissues, the ploidy of the sporogenous tissue would be 2n. And when the cells becomes metabolically active and ready to divide by meiosis, then you can say these enlarged cells and ready to divide cells are pollen mother cell. Then they perform meiosis, and once meiosis completes, they will generate 4 pollen grains. They are also called as microspores, as the size of the pollen grains are comparatively smaller than female spore, which is called as megaspore. So pollen grain, as they are produced by meiosis, their ploidy will be N. They are haploid in nature. And these are pollen grains, mind well, they are microspores. You cannot say they are gametes or they are not male gametes. Now about the structure, and one of the common question which frequently asked in the examination, that is related to the structure of anther. In the structure of anther, you can observe certain cellular structures, and that cellular structure is, that is anther. We have anther wall, and in the anther wall we can observe these 4 types of cells. One is epidermis, endothelium, middle layer, and tapetum. And tapetum cells are closest to the sporogenous tissues. That means the tapetum, consider this is the tapetum, the green one, and the green layer cell is a single layer cell. You can observe large cells but located in a single layer. And once you cross the tapetum and enter into the core area, you can find sporogenous tissue where meiosis is happening and microspores are being produced. So you have to answer that what is the role of tapetum then? Why tapetum is having large cellular structure? Sometimes it is diploid as well as polyploid cells are you can find in the tapetum. So what is the functional role of tapetum? Obviously, majority of students are not raising the hand. I have to give the answer. The role of the tapetum is the nurturing and providing nutrition and for the maturation of the pollen grain. How it helps? Another question. We know very well that pollen grains are having some sort of sticky material, and that outermost layer, which is called as exene, and the sticky material along with the exene and all that stuff is called as pollen kit. So that pollen kit, development of exene, that is having the toughest material, or you can say the best material, which is biologically cannot be hydrolyzed, or you can say uh, you can even find the fossilization of that material, that is called as sporopollenin. So that sporopollenin production and the raw material is provided by this tapetum. The overall aspect of the anther structure, typical anther structure have 4 pollen sac. Within the pollen sac, you can observe the certain area which are considered as the layers. Outermost is epidermis, the fibrous layer, then after endothelium and middle layer, and innermost would be tapetum. And once you cross the tapetum, you can observe sporogenous tissues where pollen grains are being formed, and then for the maturation, tapetum cells are helping. So this is how actually happening, and the raw material for the production of sporopollenin is provided by the tapetum. So tapetum is this way very essential for the maturation of the pollen grains once they are produced by meiosis. And another time I am telling you that pollen grains are not gametes, they are microspores. But from the pollen grains, by using the pollen grains, we can produce male gametes. Before we involve, or you can say we'll discuss the production of male gametes, we will further clarify what is there in the pollen grain. We will discuss now the structure of pollen grain. What are there, what are the components present in the pollen structure once they get matured. Okay, this is the structure. Two diagrams are there. Both of them are representing the structure of pollen grain of the angiosperm. Typical anatomical aspects and things are there which you can observe. What you observe in the structure of pollen, you can observe one of the cell which is large, which is called as tube cell. Another is the cell which is suspended in the tube cell, which is called as generative cell. So these two things are very important. In the any pollen structure, you can observe large cell, which is considerably larger in size. And another cell is smaller and it is present in this vegetative cell, particularly which is called as tube cell. So in general, you have to remember that tube cell contains generative cell. I repeat, tube cell contains generative cell. Again, question can be asked. I will definitely ask. What is that? How this generative cell is present in the tube cell? This is one question. Another question, which is much more important. When we discuss the development of pollen grain, if it is 2n, pollen mother cell, then obviously pollen grain would be having haploid nuclei. So this cell will have n, 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 n. Likewise. So pollen grain have only one nucleus. Then how it is possible that this pollen grain contains two nucleus? Is there any answer? You can raise your hand so we can unmute you, but you have to raise your hand. So this is kind of rule. If you want to give the answer, you have to raise your hand. Anyone? There is one more minute, or you can say 5-10 seconds are there. If you can. What may happen, or you can say what should happen to have this kind of two cells, or you can say two nucleus, rather. Okay, I will not give you answer. You have to search for your by own. But this is fact. What is that? In the pollen structure, you can observe two cells. One is larger one, another is smaller one. Smaller one is called as generative cell. Another one is called as tube cell. So this is the structure, which is physiologically much more important. And certain coverings are also there. One of the innermost cellular covering is called as intine. This one, this black line. And the brown line, which is tough and extremely resistive, that is exine, and it is made up of sporopollenin. Between this outermost layer, you can observe certain area where no deposition of such sporopollenin observed. So they are kind of apertures, or you can say openings, which are called as germ pore. So in the structure of pollen, you can observe germ pores. The outermost layer is exine made up of sporopollenin. And the another layer, that is intine, and this intine is nothing but it is a cell membrane of tube cell. Within this large cell, you can observe suspended another cell which is smaller in size, which is called as generative cell. So this is the typical structure of mature microspore. Still, it is not considered as male gamete. Then, this question is also important. If you can answer, please, you can answer it. Male gamete of 5. Now, I previously also asked. So this is the answer. what is the difference between male gametophyte, male gamete, and pollen grain. I repeat, I'm trying to explain what is the difference between pollen grain, male gametophyte, and male gamete, under what circumstances they can be produced. So in the pre-pollination condition, pre-pollination condition, that means pollination is not happened, anthers are, the pollen grains are still present on the flower. They are not transported to the stigma of the another flower. So they are matured and present on the flower. Now they are ready to take away by any kind of pollinating agent. In that condition, once they are matured, we had already discussed what kind of things that contains. One tube cell, another is generative cell, germ pore, exine, and intine. This is the typical structure of pollen grain. It is over here. Once they are carried away by any kind of pollinating agent, they stick on the stigma. Stigma will provide some nutritive stuff and they can activate the pollen cells. Now pollen cells, particularly tube cell, will become metabolically active, and from germ pore, from the area, this particular area which is germ pore, this intine, I repeat, this intine will be extended outside. So ये intine वाला पार्ट है कि जो हमारा सेल मेम्ब्रेन है इस सेल का, ट्यूब सेल का, वो जर्म पोर से बाहर आएगा. जब ये बाहर आएगा तब हम उसको बोलेंगे कि दिस इज पोलन ट्यूब. एंड एज the tube cell is responsible for the development of pollen tube, the name is given tube cell. That's why it is called as tube cell, or it is also called as vegetative cell. It is its nucleus. That nucleus will come forward in the tube. So development of pollen tube is important aspect which happens, and that happens when specific pollen reach to the specific stigma. Then only this thing will happen. And mind well, pollen tube will arise from germ pore, and in the germ pore you can observe uh, the presence of nucleus. That is the first nucleus which is coming towards, or you can say it is actually kind of engine. ये सबसे पहला न्यूक्लियस है. That nucleus would be of tube cell nucleus, and in the later, or you can say behind, this is the generative nucleus. You can say this cell which was generative cell is also coming out into the tube, into the pollen tube. So this tube cell nucleus is moving ahead in the tube, in the pollen tube, and followed by generative cell. Now what happens is important. This generative nucleus will divide mitotically and produce two cells. These cells are called as male gametes. So in general, this is the event entirely happens. You can say it's kind of summary. We have discussed all this stuff. Now we have pollen grain with larger cell and smaller cell. Larger is tube cell, smaller is generative cell. When it reach to the stigma, the pollen tube formation happens. This is the nucleus, which is of vegetative nucleus, also called as tube cell nucleus. And the generative cell divide mitotically to produce sperm cells. They are nothing but they are male gametes. So now, can you tell me which one is male gametophyte? I repeat, you have to raise your hand. This is ultimate understanding, where you can understand, when you can differentiate what is the difference between microspore and the male gametophyte. What is the difference between pollen grain and male gametophyte? You can say male gametophytes are the structures which contain male gamete. So this is the pollen grain, mature pollen grain, this one. Do you find any male gamete in it? No. As it doesn't contain any male gamete, that's why you cannot say this mature pollen is male gametophyte, because male gametophyte is the structure which contains male gamete. So which one is considered as male gametophyte? Germinated pollen grain, or the pollen grain which is having pollen tube, because in the pollen tube you can find male gametes. So this structure, which is the pollen present on the stigma, responsible for the development of the pollen tube and containing male gametes. This germinated pollen is called as male gametophyte. So this is simple. Mature pollen can become, I repeat, mature pollen can become male gametophyte provided specialized condition. What is that specialized condition? Okay, they need it to be transported towards stigma, where pollen tube can be germinated and uh, male gametes can be produced. So this is about male gametophyte, male gametes, microspore, the structure where microspores are being produced and everything concerned with the male component. Now coming to the female component, that is the female and that kind of thing. This is simple. This is the electron micrograph of the different kind of pollen grains. So they are real. The electron micrograph, you can observe different varieties of pollen grain and they are having typical structures. Okay, coming to the carpel, or you can say the female component of the plant. Structure of carpel, monocarpellary, multicarpellary, polycarpellary, that kind of things are there, but they are part of botanical aspect. You need to clear with that also. So in the carpel structure, you can observe stigma, style, and ovary. Within the ovary, you can observe the structure called as ovule over here. So carpel, megasporophyll, which contain megaspore. So over here, same way you have to think. What is that? If microspores are there, which are first produced, then obviously in the female component, megaspore must be produced first and then after female gamete. So this thing must be clear. Over here, we also produce first megaspore, then this megaspore will, or you can say that megaspore is capable enough to produce female gamete, or in general egg cell. So we'll look into that. Stigma style ovary, that ovary contains ovules. When we get into the structure of ovule, we have to understand what are all other components present in the ovule. So please be careful that which particular structure we are discussing here. Now I will shift to the discussion on ovule, and mind well where ovule is located. So you have to be clear where this ovule is located, and we are discussing which particular part. So when we discuss the structure of ovule, it has certain accessory components. Apart from accessory component, the most important components are present which lies in the body part of the ovule. And in the structure of ovule, you can observe nucellus cells. You can observe integuments. You can observe micropilar end. You can observe chalazal end. You can observe hilum. You can observe embryo sac. So what are nucellus cell, what are integuments, which area is micropylar, which area is chalazal end, that you need to understand. And over here, I will try to answer the things. Consider this is ovule. This particular area is considered as ovule. And the open area. And this ovule is covered by the layers. These layers are called as integuments. So these are the integuments which are actually covering, or you can say the outermost part of the ovule. To whom they cover? They cover the tissues which are called as nucellus cells. And nucellus cells are similar to the sporogenous tissues. In general, you can say nucellus cells are sporogenous tissues. They are responsible for the development of megaspore. But in the female component, in the ovule, it is considered as nucellus cells. What is the ploidy of nucellus cells? They are simply diploid. So nucellus cells, from where megaspore can be produced. Nucellus cells are covered by the protective covering called integuments, and integuments are not complete, or you can say they remain interrupted, and that area remains open. That open area of the ovule is called as micropyle. Okay, this in this structure you can observe the entire ovule. I repeat, this is the structure of ovule. Over here you can observe this part is ovary. Within the ovary you can find the presence of ovule, and ovule is protected by the uh, integuments. These integuments are not present over here, so this is open part. This end is called as micropylar end, and opposite to the micropylar end, this is called as chalazal end. So if you observe over here, this is the area which is called as micropylar end, where integuments are absent. Opposite to the micropylar end, this is chalazal end. These blue components are integuments, and within this you can observe the presence of sporogenous tissue which are called as nucellus cells. Then now question arises. We know that nucellus cells and everything. Then where is actually megaspore? Anyone? Because the development of megaspore is slightly different from the development of microspore. What happens in this? You can observe thousands of nucellus cells in the ovule, but any one cell will be considered as the megaspore developer cells, which is called as megaspore mother cell. For say example, अगर न्यूसेलस सेल्स हमारे पास 50,000 है, हाइपोथेटिकल एग्जांपल है, तो आउट ऑफ दिस 50,000 cells, any one cell will be selected randomly. Obviously, there would be some sort of mechanism, but you can say out of 50,000, any one cell will be considered to be the future megaspore. So for that, they will supply tremendous nutritive material to that particular single cell out of 50,000 cells. तो उसमें से कोई एक सेल को ही वो पसंद करेंगे और उसको न्यूट्रिटिव सप्लाई देंगे. वो सेल बड़ा होता जाएगा और it will become metabolically active and ready to divide. Now again, as it is megaspore and the nucellus cell is diploid cell, it will divide by meiosis, and meiotic division will result into 4 cells like this. So consider this is the ovule, and it is filled up with so many nucellus cells. Out of these so many nucellus cells, any one cell is divided by meiosis, and that single cell is now called as megaspore. So when we discuss microspore, we observe 4 pollen grain produced because it is because of the meiosis. So same here. In the development of megaspore, this one, this one, this one, and this one, these are the 4 megaspore which are produced. But this is not going to happen. Out of these 4, 3 will die, and one will be selected and one will become large cells. क्या होगा? मेगास्पोर बनेगा, मेगास्पोर मदर सेल. तो मेगास्पोर मदर सेल जो रहेगा वो मियोटिक डिवीजन में जाएगा. मियोटिक डिवीजन में जाने के बाद हमें 4 सेल देगा. वो ये 4 सेल है. ये जो स्टार चीज है, दिस एरिया यू कैन कंसिडर इट एज माइक्रोपाइल एंड, and this end is called as chalazal end. So micropylar end, it is the open end, and this is the another opposite part of the ovule. Out of these 4 cells, which you can say all of them are megaspore, I repeat, all 4 cells are megaspore. But out of these 4 cells, 3 megaspore will die, they will degenerated, and only one cell will grow and will be maintained, and that will become a much more larger cell. So that single large cell is called as embryo sac, and that same embryo sac is called as female gametophyte. As the name suggests, why it is called as female gametophyte? Because that single cell, that is the cell which is still left, that was megaspore, that megaspore can be considered as female gametophyte after certain event happens. What that events? The nucleus of that single cell, this one. Consider out of these 4 cells, this one, and this one degenerated. The first cell remain present. They will survive. Obviously, it is haploid, having 1 nuclei and haploid genetic content. It is having single nucleus only. It will divide by mitosis, will produce 2 nuclei. Another mitotic division will result into 4 nuclei. The third mitotic division result into 8 nuclei. Consider this is the one cell which was the megaspore. Now it contains 8 nuclei in it. Gradually, all these 8 nuclei separated in such a way that you can observe 3 cells containing one nucleus, and another 3 cells are moving towards the opposite pole. They are called as antipodal cells. These 3 cell, out of these 3 cell, one cell is egg cell. In other way, it is called as female gamete. So consider this 8 cell, this nucleus, this particular, will be covered up by cell membrane and become functional female gamete. So now we can have female gamete. Nearby these 2 nuclei, one will be covered up, another will be covered up, will produce 2 different cells, and they are called as synergids. So this is called as egg apparatus. What is there in the egg apparatus? One is egg cell, and this egg cell is having 2 synergids nearby. So synergid cells, 2, 1 egg cell, total 3 cells now you can observe. The central cell, these 2 nuclei will remain associated, will be considered as polar nuclei. So this is one another cell. And 3 nuclei converted into another 3 cells, which are all considered as antipodal cells. So in the entire structure of this single cell, which was a single cell like this was this single cell, because 3 were died. This was the single cell. That single cell is now like this, and it is now different. This single cell, you can say it's a megaspore. Now you cannot say this cell as a megaspore, because this cell contains egg. or in other word female gamete, and that's why it is called as female gametophyte. As I already discussed that female gametophytes mean what? Gametophyte, gamete bearing structure. So this structure contains female gamete. That's why it is called as female gametophyte. It is also called as embryo sac. So this is simple. What is that? In the structure of ovule, megaspore mother cells will be selected, or you can say it is the specialized cell out of the nucellus cell, that is a single cell usually that happens. That single cell becomes larger, meiotically divide to produce megaspore. That megaspore nuclei divide 3 times mitotically and produces total 8 nuclei, but total number of cell would be 1, 2, 3. The single cell common, that is polar nuclei, that would be 4, 5, 6 and 7. Total cells would be 7. So in embryo sac there would be total 8 nuclei, but the cells are 7. This is, you have to understand. Then the next thing, this is overview. Okay, this one is the selected one cell. This selected cell divide meiotically and produces 4 cells. Out of these 4 cells, 3 cells are degenerated, 1 cell remain permanently, become larger. Mitotic division resulted into 2 nuclei, then 4, then 8. These 8 nuclei separated in the form of egg apparatus, which contain female gamete, and 2 nearby cells which are synergids. 1 polar nuclei which contain 2 nuclei connected with each other, and 3 cells which are antipodal cell present in the opposite end. So this is embryo sac, and this is present in the ovule. What is the role of embryo sac? Obviously we know fertilization. What is fertilization? Fertilization is nothing but fusion of male and female gamete. Don't get confused that fertilization is the fusion of pollen grains, because pollen grains are not male gametes. Pollen grains are the spores which can be responsible for the production of male gametes. So these male gametes now has to fuse with female gamete, and that female gamete is present in the ovule near micropylar end. Why to the near micropylar end? Because this pollen tube will be transported, or you can say will be attracted towards this micropylar end. My question is, how this pollen tube determined that I has to reach to the micropylar end? Who will guide them? Who will guide this structure that this area is open, not the another area? Anyone? How pollen tube understand? How pollen tube recognize that I have to enter through this particular area? Because it may happen that based on the ovule structure may be different in different plants. So I have to enter from this area where you can find presence of egg cell. Anyone? If you know the answer, please try to raise your hand. Okay. Vakela Mansi. Okay, finally I got one answer. Yes, I'm happy. Yes,
Yes, sir.
Mansi. Yes, please. How do this pollen
Sir,
tube? Hmm.
there are some chemical receptors.
Okay, but who releases these chemicals? Because if chemical receptors are there on the pollen tube, do you mean to say? Is it so?
A pollen tube cell detect that chemicals.
Okay, then what would be the source of these chemicals? Who releases these chemicals which can be detected by the pollen tube? because in the ovule, so many different cells are present. You can observe nucellus cell, you can observe antipodal cell, you can observe egg cell, you can observe synergids. Is the egg cell releases such chemical which can be detected by the pollen tube?
I don't know. I
Yes.
don't know perfectly the name of the cell, but I know that
Okay, you
there
are
are some
partially correct.
chemicals.
Yes, because this is the movement of this pollen tube is based on chemotaxis. So this pollen tube is attracted towards chemicals. We know that. And that chemicals are not released by eggs. It is released by the synergid cells. So synergids are the cells which are along with the egg cell. This is egg apparatus and close to the micropylar end. And these synergids are releasing these chemicals and they are sensed by the pollen tube. And this way pollen tubes are actually guided towards these chemicals and they enter into the micropylar end. Now another question. Now you are charged, I think. As this is a tube and which contain nucleus, now it contains two male gametes. But as it is a tube, then how these pollen male gametes are released into this area? Because we know that male gamete has to fuse with the female gamete, but these male gametes are encapsulated in the pollen tube. तो ये तो पोलन ट्यूब के अंदर है ना, तो पोलन ट्यूब में से ये कैसे निकलेंगे? Anyone? So many things are there which can be discussed, and 1 hour is definitely less, extremely less to understand the typical concepts. Anyone? आपको पता चला ना क्वेश्चन क्या है? अगर ये सेल पोलन ट्यूब के अंदर है तो फिर ये पोलन ट्यूब में से निकलेंगे कैसे? क्योंकि पोलन ट्यूब हमें पता है कि इट्स काइंड ऑफ स्ट्रक्चर व्हिच इज कैप्सुलेटेड, हैविंग सेल मेम्ब्रेन एंड ऑल दैट स्टफ.
Sir,
हाँ बोलिए.
first of all, tube cell fuse with synergid cell, and uh, that their gametes fused and form zygote.
If they fuse with the synergids, then how these male gametes can interact or can be fused with female gamete? Because as you say that it is interacting with synergid. What is the role of
The,
synergid? Yes, please.
the only way, provide way
Okay, it will
to
guide. Okay, it will guide this pollen tube towards egg cell. Is it so?
yes, sir.
Okay, now listen carefully. This would be the last understanding. So many things are still left, but you can read by your own and you can discuss. What happens once this pollen tube enters in this particular area? Synergids is actually doing osmotic lysis. So many water content hypotonic solution. Because of the hypotonic solution, this pollen tube will be enlarged in this area, and this is helped by the synergid cells. And as the osmotic lysis happens, you can literally understand that this pollen tube, once it enters through the micropylar end, it will burst inside. Once it get burst inside, now these two nuclei can be released into the embryo sac. Now these two nuclei have access to female gamete and to this polar nuclei. This polar nuclei will be fertilized by one male gamete. Another male gamete is fusing with the egg cell, which will be responsible for zygote formation. And this 3N structure will be responsible for the endosperm formation, which is called as primary endosperm nucleus. So this is it. This is up to the fertilization. And as two male gametes are fertilizing one to the egg cell and to the another polar nuclei, that's why it is called as double fertilization. Okay, thank you guys. Thanks for listening.
Thank you very much, sir. So we are running short of time. So few things as I listen, few things still remains. But as we are running short of time, so we have to finish or end up this session of Mayur sir. And now coming to the next in the series of lectures, last but not the least, our next lecture will be of photosynthesis, and it will be delivered by Dr. Nishant Junarkar sir. He is an HOD in microbiology department. He has qualified so many competitive exams, and he will definitely guide you in cracking those examinations. So just I am giving rights to sir. Just a minute. Hello, Nishant sir.
Yes, sir. Thank you, sir.
Okay.
I'm just loading my PPT.
Yes. Okay, sir. It's visible.
Even now. Is it in the slide mode,
Yes, sir.
presentation mode?
Yeah, yeah. Yes, sir.
Okay. So,
Okay.
thank you, sir. So, I'm thankful to the Atmiya University for giving me the opportunity to deliver the lecture in Gsbtm sponsored e-workshop for third year UG students. And my topic for today's discussion is photosynthesis. We'll go in details on the photosynthesis. We'll have a look at certain questions because this topic is very important and many questions are asked in the competitive examinations from this topic. So one of the question is listed, which indicates that whether the sucrose and starch, which are synthesized in the plant cells, where the synthesis of these components occur or these molecules occurs. Sucrose synthesis occurs where, and the starch synthesis occurs in which organelles. So you have to identify the correct combination among the given options. Another question is based on energy transfer that occurs in the photosynthesis, in which pathway or what is the actual format of the electron transfer reactions that occur during the photosynthesis, during the light reaction, that you have to identify the correct combination. Then the third question which I have selected is based on the different statements on photosynthesis, and you have to identify among the given statements which of the statement on photosynthesis is false. And one question is on the C4 plants. Why C4 plants show very high rate of photosynthesis as compared to C3 plants? So these are certain questions which we'll discuss at the end of our discussion on photosynthesis. I will cover some of the aspects regarding the photosynthesis, which includes photosynthetic apparatus, then light reactions, electron transport chain that occurs during the light reactions, dark reactions, which involve the CO2 fixation pathways, photorespiration, and C3 and CAM pathway. So life on Earth ultimately depends on energy which is derived from the sun. And photosynthesis is the only process of biological importance that can harvest this energy. The term photosynthesis means literally synthesis using light. Here, light energy drives the synthesis of carbohydrates from carbon dioxide and water, resulting in the generation of oxygen. So if the empirical formula of the photosynthesis can be given in this manner: 6 CO2 molecules and 6 water molecules are used in synthesis of one carbohydrate molecule, and 6 molecular oxygen molecules are liberated. The energy stored in these molecules can be used later to power cellular processes in the plant and can serve as the energy source for all forms of life. Now, which cells are involved in photosynthesis? The most active photosynthetic tissue in higher plants is the mesophyll of leaves. Mesophyll cells have many chloroplasts which contain the specialized light-absorbing green pigments called as chlorophylls. The photosynthetic apparatus involves chloroplasts, photosynthetic pigments such as chlorophyll and other accessory light-gathering pigments, and the integral protein complexes which are involved in the electron transport chain. So all these three make up the photosynthetic apparatus. Chloroplast, it is the site of photosynthesis and it is a double membranous organelle. The fluid inside this organelle is called as stroma. In this stroma, there are several tiny membranous sacs which are called as thylakoids. Thylakoids, they are stacked in groups and each group is called as granum. There are several grana in each chloroplast and chloroplast can have 10 to 100 grana which are interconnected to each other by unstacked stromal lamellae. So here you can see the figure of the Gsbtm cells, and these cells contain several chloroplasts, and the section of the chloroplast is shown where the two membranes are there, and inside the chloroplast the thylakoid discs are stacked over each other to form grana, and these grana are interconnected to each other through stromal lamellae. The another important aspect of the photosynthetic apparatus is the integral membrane proteins. So the thylakoid membranes contains proteins which are integrated into its membrane. So here you can see the amino terminus of these protein complexes are oriented towards the stroma, whereas carboxyl terminus of the protein complexes are oriented towards the lumen of the thylakoids. So this is how the integral membrane proteins are integrated into the thylakoid membrane. The light harvesting photosynthetic pigment molecules involves chlorophyll, which is a porphyrin ring structure containing compound, and number of different types of chlorophylls they exist. Different chlorophylls, they have different absorption spectra. Chlorophyll pigments are located within specialized membranes. In case of eukaryotes, they are called as thylakoid membranes, and in prokaryotes, these chlorophyll pigments are integrated into the cytoplasmic membrane. The chlorophylls are distributed widely among the plants and the photosynthetic bacteria. The distribution pattern is a typical type. Chlorophyll A and B are abundant in green plants, whereas chlorophyll C and D are found in some protists and cyanobacteria. Among different types of bacteriochlorophylls which are found among the prokaryotes, the bacteriochlorophyll type A is most widely distributed among the photosynthetic bacteria. If we look at the structure of the chlorophyll A and bacteriochlorophyll A, both have almost similar structure, but in the cyclopentane ring A, there is a different functional group, whereas the acetyl group is there on the cyclopentane ring A, whereas the D ring is reduced in case of bacteriochlorophyll. So these are certain differences in the bacteriochlorophyll and chlorophyll, which also results in the differences in the absorption spectral characteristics. So the absorption spectra of the chlorophyll A and bacteriochlorophyll A are shown in this figure, where we can see that the bacteriochlorophyll A absorbs maximally in the far red region or near infrared region, whereas in the case of chlorophyll A, it absorbs maximally at 680 as well as at 430 nanometer. So these are the absorption spectral characteristics of chlorophyll and bacteriochlorophyll. In addition to chlorophyll, the accessory pigments are also found, which includes carotenoids and phycobilins. Carotenoids are long-chain hydrophobic compounds. These are lipid soluble and responsible for yellow coloration of leaves. They perform two functions as an accessory light harvesting pigment, and they carry out the protection of chlorophyll from photooxidative damage, which is called as solarization. Phycobilins, these are abundantly found in red algae and cyanobacteria. They are non-cyclic linear tetrapyroles. That is the structures that may be considered as a chlorophyll molecule whose ring structure is opened up and the magnesium ion is discarded. These pigments are soluble in water. So these are the structures of carotenoids and phycobilin or bilin pigments. So you can see over here the different repetitive isoprene units are present in the structure of beta carotene, which is one kind of carotenoid. And the bilin pigment, phycoerythrobilin, is shown over here in this structure. The excited chlorophyll molecule, upon absorption of light, has 4 alternative pathways to dispose of the available energy. So these different paths are shown in this figure. One of the option is that the excited chlorophyll molecule can dispose of the excess energy in form of fluorescence, and then it can come to its ground state. Or the excited chlorophyll molecule can dispense of the excess energy in form of heat, and the heat is dissipated, and the chlorophyll molecule then enters into the ground state. Another third option is that the excited chlorophyll molecule can result in the formation of reactive oxygen species. And the most important path or the option is the photochemistry, in which the excited chlorophyll molecule can drive the occurrence of several other chemical reactions which may require more energy. So photochemical reactions are the reactions which are most probably the fastest reactions that occur in the living organisms. So these are the 4 options available to the excited chlorophyll molecule. The light harvesting complexes are the another part of the photosynthetic apparatus, and in natural photosynthetic systems, the pigment molecules are bound to polypeptide forming pigment protein complexes called as photosystems, or they are often called as pigment systems. The photosystems have 2 components: reaction centers and antenna pigments. Reaction centers, they participate directly in the conversion of light energy to ATP, whereas antenna pigments, they channel or funnel the light energy to reaction centers. So especially when the light intensity is very low, then in such situation, the antenna pigments are very helpful in getting the reaction center chlorophyll molecule to get excited. So this is the arrangement of the light harvesting complex and the reaction centers. So this is how the photosystems are arranged. And the energy transfer occurs from the chlorophyll molecules of the light harvesting complexes. They absorb light energy and then they channel this absorbed light energy towards the chlorophyll of the reaction center, which upon absorption of the energy, it gets excited and donates the electron to the next electron carrier, and through those electron carriers, the electrons, they transport to different carriers. So 2 types of photosystems are found, PS1 and PS2. PS1 is driven by light of wavelength of 700 nanometer or less. Photochemical reaction center is designated as P700 because it absorbs wavelength maximum at 700 nanometer. PS2 is the photosystem which is driven by light of wavelength shorter than 690 nanometer. Its absorption maxima is 680 nanometer and hence referred as P680. So these photosystem 1 and 2, they are specially separated in the thylakoid membrane. You can see the figure of the distribution of the PS2 and PS1 system. So here the ocean green color is that of PS1 and the green color is that of PS2. So you can see that the PS1 is found in the non-apparest regions. Non-apparest regions are the regions of the thylakoid membranes which are not in direct contact with the other thylakoid membranes. So these are the regions where you can find the non-apparest regions, whereas the apparest regions are those in which the thylakoid disc membranes, they are in direct contact to each other. So you can see that PS2 is found in apparest and non-apparest regions, whereas PS1 is mostly found in the non-apparest regions. So this is to be remembered. So this is how the arrangement of the pigments in the thylakoid membranes occur. So the chlorophyll molecules are associated with the protein complexes, and this photosystem complex is formed, and the chlorophyll A molecules are associated tight closely with the protein complexes. And in addition to the chlorophyll molecule, the accessory pigments such as carotenoids also are found in these complexes. The patterns of photosynthesis involves oxygenic photosynthesis and anoxygenic photosynthesis. In case of oxygenic photosynthesis, the water molecule is splitted in presence of light. So here the electrons that are liberated from water molecule are then transferred through various electron carriers, and the NADPH is synthesized. NADPH and ATP are made available, which are used for the synthesis of the organic matter using CO2 as the starting material. So CO2 fixation is carried out with the help of NADPH and ATP that are synthesized during the light reactions. In case of anoxygenic photosynthesis, the electron donor is other than water molecule, such as reduced sulfur compounds, hydrogen sulfide, elemental sulfur. These can serve as electron donors, and the NADPH and ATP, which is synthesized during the light reactions, can be used for the fixation of the carbon dioxide to synthesize the organic matter. So anoxygenic photosynthesis is found in at least 4 phyla of bacteria. The electron transport reactions that occur in the reaction center of anoxygenic phototropes, reducing power for CO2 fixation comes from reductants present in the environment, such as hydrogen sulfide, ferrous iron, or nitrite. These organisms, they require reverse electron transport flow for NADH production in purple phototropes, especially because the energy is not enough to carry out the synthesis of the NADH, because the reduction potential value of the NADH is different from that of the electron donor. So in such case, the reverse electron flow is required, which consumes some of the energy. So these are the membranes of the anoxygenic phototropes that are shown over here. So several vesicular structures are found in the purple bacteria, and the specialized vesicles called as chromatophores are found in these organisms. So these are the specialized structures which are exclusively found in the anoxygenic phototropes. Example is that of Ectothiorodosphira, which is a purple bacterium, which has lamellar membranous structures that are found in their cells. So here is the example of electron flow in the anoxygenic photosynthesis. So bacteriochlorophyll in the reaction center in the photosystem P870, when it absorbs light near the red or infrared region, it gets excited, and the excited chlorophyll molecule then donates electron to bacteriophyophytin. The bacteriophyophytin then gives electrons to quinones, quinone A, then to quinone B, and through quinones, the electron is transported to the cytochrome BC1 complex. And from cytochrome BC1 complex, the electron goes to cytochrome C2, and from cytochrome C2, the electrons come back to bacteriochlorophyll of P870. So here, for generation of the NADPH, the reverse electron flow is required at the level of quinones. So from quinones, the reverse electron flow to NADP plus occurs, resulting in generation of the reducing power. Now this generates the proton motive force, and the proton motive force, now because at several points, especially over here at the level of quinones, the protons are pumped into the periplasm of the bacteria, and this generates the proton gradient, which is used for the synthesis of ATP through membrane-bound ATP synthesis. In case of oxygenic photosynthesis, the Gsbtm is found. This involves two photosystems, photosystem 1 and photosystem 2. So, the chlorophyll molecule of photosystem 1 is involved. Photosystem 2 is involved in the initiation of this electron transfer chain reaction, where upon absorption of in presence of light, the oxygen evolving complex splits water, and the electron from the oxygen molecule is accepted by a electron acceptor YZ, which gives electrons to the chlorophyll molecule, which had previously given electrons to the when upon excitation it had given electrons to pheophytene. So this excited chlorophyll molecule, which had given electrons to the pheophytene, then gets reduced by accepting the electrons from the electron donor YZ. That is how it gets reduced again. So excited chlorophyll molecule, it gives electrons to pheophytene. From pheophytene, the electron goes to quinone A, then to quinone B, and the electron is then accepted by cytochrome B6F complex, which is a complex containing cytochrome B, then FESR protein, cytochrome F. These are the certain molecules which are found in this cytochrome B6F complex. From cytochrome B6F complex, the electron goes to plastocyanine, and from plastocyanine, the electron are received by the chlorophyll molecules, which had chlorophyll molecules of PS1, which had previously donated electrons to the chlorophyll A molecule designated as A0, acceptor A0 and A1. So, the chlorophyll molecule of PS1, when it absorbs light, it gets excited, and the excited chlorophyll molecule of PS1 gives electrons to A0, and then from A0 molecule, the electron goes to A1 molecule, and then the electrons are accepted by iron sulfur protein complex FeSX-A and FeS-B. From iron sulfur protein complexes, the electrons are received by ferredoxin, and with the help of FNR enzyme, the electron is given to NADP plus, and the NADP plus is reduced to NADPH. So reducing power is generated. Now, when reducing power is enough, in such case, the ferredoxin can give electrons to cytochrome B6F complex, which gives electrons to plastocyanine, and the electron come back again to the chlorophyll molecule of PS1 system. So that is how the cyclic electron flow occurs. We'll talk about that again. Some herbicides block electron transport chain, such as DCMU, paraquat. DCMU, also called as diuron, and its chemical name is dichlorophenyl dimethylurea. So here the DCMU blocks the electron path from quinone A to quinone B. So this is how it will function. It will block the electron transport chain reaction at the level of quinones. Then paraquat is involved in blocking the electrons from the photosystem 1 to NADP plus, and that is how these herbicides can inhibit the growth of weeds. So here you can see that during the transport of electrons from the PS2 to PS1 and from PS1 to NADP plus, the protons are pumped into the lumen, and the proton gradient is created. This proton gradient which is created is used for the synthesis of ATP through membrane bound ATP synthase enzyme. So here the proton are brought into the stroma through the ATP synthase molecule. the protons, they fall on this C disk, and the turbine rotates, and that results in the attachment of the inorganic phosphate with the ADP, resulting in formation of ATP. So here is the cyclic electron flow that I talked earlier, that when the NADP plus levels are low and NADPH levels are high, the electrons from the P700 center, they are returned to the chlorophyll molecule of P700 back via cytochrome B6F complex. So here, instead of giving electrons to NADP plus, ferredoxin gives electrons to cytochrome B6F, and the cytochrome B6F complex gives electrons to plastocyanin, and plastocyanin returns electron back to chlorophyll of P700 for PS1 system. And so this is how the cyclic electron flow occurs when NADPH levels are high. So here this pathway can result in synthesis of ATP. It can continue the synthesis of ATP, but NADPH production will not occur through cyclic electron flow or cyclic photophosphorylation. Water is oxidized to molecular oxygen by photosystem 2. So here water is a very stable molecule, and oxidation of water to form molecular oxygen is very difficult, and the photosynthetic oxygen evolving complex is the only known biochemical system which carries out this reaction. Photosynthetic oxygen evolution is also the source of almost all the oxygen that is present in the Earth's atmosphere. The protons produced by water oxidation are released into the lumen of the thylakoid, not directly into the stromal compartment. They are released into the lumen because of the vectorial nature of the membrane and the fact that the oxygen evolving complex is located on the interior side of the thylakoid membrane. These protons are eventually transferred from the lumen to the stroma by translocation through ATP synthase enzyme. So here, this is how the protons, they fall onto the C rings of the ATP synthase CF0 component, and the C rings, they rotate, so like a turbine. So you can just imagine a turbine which is getting rotated due to falling of the protons onto it, and that causes the phosphorylation of ADP, because the rotation of these C rings causes the F1 components, okay, to rotate, and the ADP gets phosphorylated to ATP, is the inorganic phosphate. So this is how the ATP synthesis occurs by the membrane bound chloroplast ATP synthase enzyme. So here, if we look at the reactions that occur in the chloroplast, the light reactions and dark reactions occurs. Light reactions results in the synthesis of NADPH and ATP, which are used for the synthesis of the organic compounds through Calvin cycle. So Calvin cycle reactions are regarded as the dark reactions because they don't require the light to be present for them to occur, but they are indirectly dependent on the products of the light reaction. And these dark reactions, they occur in stroma. NADPH and ATP are available in the stroma. So through Calvin cycle, the organic compound is synthesized. For example, a sugar is shown, which can be then transported outside the chloroplast and can be distributed to all the cells. So these sugars are used for cellular respiration, for the synthesis of polymers such as cellulose or starch and other organic compounds. Several questions in several competitive exams, the questions may be asked from the experiments carried out by Jengendorf and co-workers, who proved that the ATP synthesis occurs through chemiosmotic mechanism. In their experiments, they harvested the chloroplast and chloroplast thylakoids, and they took the included the thylakoids into the buffered medium having pH, 4. Now, and they later on allowed the chloroplast thylakoids to get equilibrated. So inside the lumen, the protons were transferred till the pH inside the lumen and outside the thylakoid base becomes equal. Then after equilibration, the thylakoids are transferred into the buffer having pH 8, and into that flask, the ADP and inorganic phosphate, when it is added, it can cause the synthesis of ATP even in absence of light. So even in dark, with the help of thylakoids, the ATP synthesis can occur. So this experiment proved that the ATP synthesis occurs through chemiosmotic mechanism. Role of carotenoids and xanthophylls are very important in protection of the cells from photooxidative damage. So here the photons which are absorbed, if the photon intensity is very high, then excess of photons are released in form of heat. This becomes the first line of defense. Then remaining photons can result in formation of the toxic photoproducts such as the triplet state of chlorophyll, and superoxides may be generated, singlet oxygen may be generated, hydrogen peroxide. So these are all toxic photoproducts which can damage to the D1 protein of photosystem 2. So here the they can damage to the PS2 system. So here the second line of defense occurs, in which the scavenging of these triplet, these phototoxic products is carried out by carotenoids and the enzymes such as superoxide dismutase and ascorbate, and these molecules, they can scavenge these phototoxic products and they can protect the D1 protein of photosystem 2 so that the photo inhibition doesn't occur. But even if still the D1 protein gets oxidized, then it causes the photo inhibition. The oxidized D1 protein can be again repaired, or the new synthesis of the D1 protein can be carried out. So this is how the carotenoids and xanthophylls, they protect the chlorophylls from the photooxidative damage which can occur at the high intensity of the photons. Let us now come to the dark reaction. Dark reaction involves the Kelvin cycle. It is named for its discoverer Melvin Kelvin. So here the fixation of CO2 occurs into the cellular material for autotrophic growth. It requires NADPH, ATP, a ribulose bisphosphate carboxylase oxygenase enzyme called as Rubisco, and phosphoribulokinase. These are the key enzymes, Rubisco and phosphoribulokinase. 6 molecules of CO2 are required to make one molecule of hexose sugar, such as glucose. The key reactions of Kelvin cycle are shown, where the starting material is the ribulose 1,5 bisphosphate. So ribulose 1,5 bisphosphate is acted upon by Rubisco enzyme, and an unstable intermediate is formed, which is splitted into 2 molecules of phosphoglyceric acid. From this phosphoglyceric acid molecules, the phosphoglyceric acid molecule is phosphorylated to form 1,3-bisphosphoglyceric acid, and this 1,3-bisphosphoglyceric acid is reduced to glyceraldehyde 3-phosphate, which is used for biosynthesis. Some of the molecules of glyceraldehyde 3-phosphate are used for regeneration of ribulose 5-phosphate, which is used for regeneration of the starting material, ribulose bisphosphate, with the help of the key enzyme phosphoribulokinase. So once the ribulose bisphosphate is regenerated, the cycle is repeated. So here is the Kelvin cycle shown, where the Kelvin cycle is resulting in the synthesis of a 6-carbon compound. So for synthesis of a 6-carbon compound, net 6 carbon dioxide molecules will be required. So from 6 carbon dioxide molecules and 6 starting material, that is 6 molecules of ribulose 1,5 bisphosphate, the 12 molecules of 3-phosphoglyceric acid is formed. These 3 phosphoglycerate molecules are phosphorylated to form 1,3-bis-phosphoglycerate. So 12 molecules of 1,3-bis-phosphoglycerate are now made available, which are reduced to 12 molecules of glyceraldehyde 3-phosphate. So here we have 36 carbons, 6 from the CO2 and the 6 of the 30 carbons of the pentose sugar ribulose 1,5-bisphosphate. So total 36 carbons will be available from the 12 glyceraldehyde 3-phosphate molecules. Out of these 12 glyceraldehyde 3-phosphate molecules, 2 glyceraldehyde 3-phosphate molecules are used for the synthesis of fructose 6-phosphate, which is a hexose sugar, and 10 glyceraldehyde 3-phosphate molecules are used for the regeneration of ribulose 1,5-bisphosphate molecule, which is then made available to carry out the another round of the Calvin cycle. And the fructose 6-phosphate, which is synthesized over here, can be used for the synthesis of other organic compounds. So overall stoichiometry of this Calvin cycle is shown in this slide. 6 molecules of CO2 requires 12 NADPH molecules and 18 ATP molecules, resulting in synthesis of 1 hexose sugar. And the 12 NADP plus and 18 ADP molecules are released. So here you have to remember how many CO2 molecules and NADPH and ATP are required for the fixation of the CO2 through Calvin cycle. Rubisco is the key enzyme of this pathway, that is Calvin cycle. It catalyzes the carboxylation of ribulose 1,5-bisphosphate. The enzyme also has an oxygenase activity in which the oxygen competes with the carbon dioxide for the common substrate ribulose 1,5-bisphosphate. So if the oxygen is lower, then photorespiration will occur. And if CO2 levels are high, then the CO2 fixation will occur by the Rubisco enzyme. So the two properties of the carboxylase reaction are especially important. Number one, the negative change in the free energy associated with the carboxylation of ribulose 1,5-bisphosphate is large. Thus, the forward reaction is strongly favored. The affinity of Rubisco for CO2 is sufficiently high to ensure rapid carboxylation even at the low concentrations of carbon dioxide found in photosynthetic cells. Rubisco is very abundant, representing up to 40% of the total soluble protein of most leaves. The concentration of Rubisco active sites within the chloroplastoma is calculated to be about 4 millimolar or about 500 times greater than the concentration of its substrate, that is CO2. Now let's have a look again at the ratio of CO2, NADPH and ATP that are required for the fixation of carbon dioxide through Calvin cycle. So many questions are asked on this ratio, that for the synthesis of erythro sugar, how many NADPH and how many ATP will be required. So you have to remember the ratio of CO2 is to NADPH is to ATP. So if the ratio is given in this sequence, then you have to remember 1:2:3 for CO2 is to NADPH is to ATP. So this is the ratio. And if the sequence is changed, if the sequence is given that what ratio of the CO2, ATP and NADPH are required for the synthesis of a glucose molecule, then if the sequence is given that CO2 is to ATP is to NADPH, then you have to consider this ratio, that is 1:3:2. Now how to remember these ratios? So you can just make illogical formulas. For example, in Gujarati you can say a kona 123 rupiya છે. Okay, Kona means CNA. 123, 1:2:3. Okay, or you can just remember at CNA 123 and CAN, CAN, C for carbon dioxide, A for ATP, N for NADPH. I can dial 132 or I can score 132 runs easily in a cricket match. Okay, so you can remember such formula using this illogical formula, and you can remember the sequence of this ratio. Okay, so I can dial 132 and CNA 1, 2, 3. Okay, so this is how you should remember. This is very important in solving some of the questions based on this ratio. Starch and sucrose synthesis sites. Here, the starch is synthesized in chloroplast. You have to remember in which part of the chloroplast its synthesis occurs in stroma, whereas sucrose is synthesized in the cytosol of the plant cell. This is very important to remember. Photorespiration is the another reaction that can occur when the oxygen levels are high compared to CO2 levels. So photorespiration generally occurs when temperature is high and CO2 levels are low. So when temperature is high and CO2 levels are low, in such case, the oxygen levels will be more compared to CO2, because as temperature is high, the stomatas will be closed, and the slowly and gradually the CO2 will be consumed, and at a certain point the CO2 levels will drop such that oxygen levels will be high, and under such situation the Rubisco enzyme converts ribulose 1,5-bisphosphate in presence of molecular oxygen into 3-phosphoglyceric acid and phosphoglycolate. So here this is the product of the photooxidation pathway. Phosphoglycolate and 3-phosphoglycerate is formed through Rubisco enzyme, which used to carry out the carboxylation reaction in presence of CO2 when it is present at high levels. But when the CO2 levels drop, then the different products are formed by the same reaction, by the same enzyme. So Rubisco converts ribulose 1,5-bisphosphate into phosphoglycolate and 3-phosphoglycerate. Now this 2-phosphoglycolate that is formed in the reaction catalyzed by Rubisco in presence of high concentration of oxygen and low concentration of CO2, then this 2-phosphoglycolate is converted into glycolate, which is then transported into peroxisome, where the glycolate is converted into glyoxylate, and glyoxylate is converted into glycine. Glycine is then transported into mitochondria, where from 2 molecules of glycine, the decarboxylation and the arrangement reactions occur, carrying out condensation reaction occurs, resulting in the liberation of one CO2 molecule and synthesis of serine. Serine is then transported into peroxisome, where it is converted into hydroxypyruvate, which in turn is converted into glycerate. And glycerate is then transported into this chloroplast stroma, where it is converted into 3-phosphoglycerate, which enters into the Calvin cycle. So here there is the net carbon loss over here through photorespiration pathway. So when the photorespiration pathway is high, the productivity of the plant is less. So this photorespiration is generally seen in the C3 plants. C3 plants are those in which the first product is a 3-carbon acid. So here the growth of the plant is detected or decided by the balance between the electron transport and the Calvin cycle, as well as the photorespiration reaction, which is also called as C2 oxidative photosynthetic carbon cycle. So here if the CO2 fixation, that is Calvin cycle, predominates, then the net carbon gain will be there and the productivity will be more. But if the photorespiration dominates, then the productivity will be less. So to deal with this, there are several plants which have developed certain mechanisms for concentrating the CO2 in their cells. So these include C4 plants or CAM plants. Certain microbes, they have the CO2 pumps in their plasma membrane. So these organisms, at the concentration of CO2 found in the aquatic environments, Rubisco operates far below its maximal specific activity. Marine and freshwater organisms, they overcome this drawback by accumulating inorganic carbon by the use of CO2 and bicarbonate pumps at the plasma membrane. ATP derived from the light reactions, it provides the energy necessary for the active uptake of CO2 and bicarbonate. So this is how the CO2 pumps help in concentrating the CO2 inside the cells in case of photosynthetic bacteria, especially the aquatic, which are found in the aquatic environments. Whereas in C4 and chem plants, the different mechanism is there. C4 plants, which includes maize, sugarcane, sorghum. So these are some examples of C4 plants. Why they are called as C4 plants? Because the first stable product of CO2 fixation is a 4-carbon acid. Now the leaves of these plants, they have a specialized anatomy called as Krenz anatomy, in which the garland-like appearance is found in the leaves, which is called as Krenz anatomy. So here the mesophyll cells, they surround the bundle sheath cells, and these the actual CO2 fixation occurs in the bundle sheath cells. So we'll see about the C4 plants. So the salient features of the C4 cycle involves the fixation of CO2 by the carboxylation of phosphoenol pyruvate in the mesophyll cells to form a C4 acid in form of malate or aspartate or both. Then this malate is transported to the bundle sheath cells, where the decarboxylation of malic acid occurs within the bundle sheath cells and generation of CO2 occurs, which is then reduced to carbohydrate via Calvin cycle. The transport of C3 acid, that is pyruvate, or alanine, that is formed by the decarboxylation step, occurs back to the mesophilous cells, and regeneration of the CO2 acceptor phosphoenol pyruvate occurs. So the pathway of C4 photosynthesis, which is also called as Hatch and Slack pathway, is shown, where CO2 is concentrated in form of bicarbonate, and the bicarbonate then enters into the chloroplast of the mesophilous cells, where it is acted upon by PEP carboxylase enzyme. The first acceptor molecule is phosphoenol pyruvate over here, and it is acted upon by PEP carboxylase and not Rubisco enzyme. So phosphoenol pyruvate, when it is carboxylated, it forms oxaloacetate, which is a C4 compound, and that's why it is called as C4 photosynthesis. Oxaloacetate is then reduced to malate. The malate is then transported into the bundle sheath. Inside the bundle sheath cells, in the chloroplast of the bundle sheath cells, the malate is decarboxylated to carbon dioxide and pyruvate. So the carbon dioxide that is released over here then enters into the Calvin cycle, which operates in the bundle sheath cells. The pyruvate, which is found over here, is transported into the mesophilous cells through plasmodesmata, and the pyruvate is converted into phosphoenol pyruvate, which is the starting material for the C4 photosynthesis. So this is how phosphoenol pyruvate is regenerated. So in C4 plants, the photorespiration is very reduced, or you can say it is almost absent, and that is the reason why the C4 plants have higher productivity compared to C3 plants. So this is the same figure indicating the generalized pathway of the C4 photosynthesis. In hot, dry climates, the C4 cycle reduces the photorespiration and water loss. Two features of the C4 cycle in C4 plants overcome the deleterious effects of higher temperature on photosynthesis. that were noted earlier. First, the affinity of PEP carboxylase for its substrate bicarbonate ions is sufficiently high that the enzyme is saturated by bicarbonate ions in equilibrium with air levels of carbon dioxide. Further, because the substrate is bicarbonate ions, oxygen is not a competitor in this reaction. This high activity of PB carboxylase enables C4 plants to reduce the stomatal aperture and thereby conserve water while fixing CO2 at rates equal to or greater than that of the C3 plants. The second beneficial feature is the suppression of photorespiration resulting from the concentration of CO2 in the bundle sheath cells. As these plants, they keep on concentrating CO2. So here photorespiration generally doesn't operate, or it is generally absent, we can say, in the C4 plants. Another pathway is CHEM pathway, which is found in the plants which belongs to the member of Crucilaceae family. And this is also found in some of the members of the angiosperms. Especially these are succulent plants, which includes several cacti, then pineapple, vanilla, agave. These are some examples of the plants which operate CHEM pathway. So here in all these plants, the CO2 is assimilated at night. So here at night the temperatures are low and so stomatas are open. Whereas during the day the stomatas are closed because the temperature is higher. So at night, stomatas are open and so atmospheric CO2 can be taken up and the CO2 is converted into bicarbonate ions, which is acted upon by PB carboxylase to convert phosphoenol pyruvate and bicarbonate ions into oxaloacetate. Oxaloacetate is converted into malate, and in the same cell, the malic acid is preserved or it is concentrated into the food vacuole at night. So the continuous supply of phosphoenol pyruvate can be achieved through the hydrolysis of the starch, which is converted into glucose, and glucose can be converted into triose phosphate, which can be converted into phosphoenol pyruvate. So that metabolism can glycolytic metabolism can result in the generation of phosphoenol pyruvate during the night time, and the continuous supply of phosphoenol pyruvate can be done so that more and more malic acid is formed and it can be stored into the vacuole. Then during the daytime, the stomatas are closed. So during the day, from the vacuole, the malic acid is then transported out and is transported into the stroma of the chloroplast, where the NADP plus malic enzyme converts malate into pyruvate and carbon dioxide. Pyruvate is then used for the synthesis of starch. So again, starch is replenished. Whereas CO2, which is liberated through decarboxylation reaction, cannot escape out of the cell because stomatas are closed. And so CO2 can be used now for fixation through Kelvin cycle. So Kelvin cycle operates during the day period within the same cell, whereas the malic acid synthesis or and accumulation occurs during the night. So this is how the Kelvin cycle will operate in the CHEM plants during the day when the stomatas are closed. So this is how they can overcome the photorespiration mechanism that can operate when the oxygen levels are high compared to CO2 levels. So here is the comparison of C3, C4 and CHEM pathways. So whether the Krebs anatomy is found in C3 plants, C4 plants and CHEM plants. So in C3 plants, the Krebs anatomy is absent. C4 plants, Krebs anatomy is found, whereas in CHEM plants, the Krebs anatomy is absent. The ratio of CO2 is to ATP is to NADPH is shown, where it is 1:3:2. In C4 plants, it is 1:5:2. That is 5 ATP molecules and 2 NADPH molecules are required for fixation of one carbon dioxide molecule. In case of chem plants, approximately the ratio is 1:6.5:2. Then the carboxylating enzyme. In case of C3 plant, it is the Rubisco enzyme. Rubisco carries out the carboxylation reaction, whereas in C4 plants, in mesophyll tissue, in the mesophilous cells, PEP carboxylase carries out the carboxylation reaction, and in bundle sheath cell, Rubisco is the carboxylating enzyme. In case of chem plants, during day, the Rubisco is the carboxylase enzyme, whereas in night, PEP carboxylase is the carboxylating enzyme. Then initial CO2 acceptor. Which is the initial CO2 acceptor? In C3 plants, it is the ribulose 1,5-bisphosphate. In case of C4 and chem plants, phosphoenol pyruvate are the initial CO2 acceptors. Then first stable product. In case of C3 plants, it is the 3-phosphoglyceric acid, whereas in case of C4 and chem plants, the oxaloacetate is the first stable product, and that's why this is called as C4 photosynthesis. Optimum temperature for photosynthesis. In case of C3 plants, it is 15 to 25 degrees Celsius. For C4 plants, it is 30 to 40 degrees Celsius. And in chem plants, it is more than 40 degrees Celsius. CO2 compensation point in terms of ppm is 30 to 70 ppm for C3 plants, 0 to 10 ppm for C4 plants, and 0 to 5 in dark. So you can see even at very low partial pressure of CO2, the C4 plants can carry out the CO2 fixation compared to the C3 plants, which requires 30 to 70 ppm of carbon dioxide levels for carboxylation reaction to occur. Photorespiration, whether it is present or absent, in case of C3 plants, it is present. In case of C4 plants, it is not easily detectable, whereas in chem plants, it can occur during the daytime, in the afternoon, especially when the temperature is very high. Kelvin cycle, whether it is operative, in C3 plants, it is operative alone. In case of C4 plants, it is operative along with the Hatch and Slack cycle, and in chem plants also, the C3 and Hatch and Slack cycle both operates in the same cell. So these are the comparative account of the C3, C4 and chem pathways. So this was all about the photosynthesis, and now we'll have a look at some of the questions based on photosynthesis. The photosynthetic, so the first question is there on the screen. The photosynthetic assimilation of atmospheric CO2 by leaves yield sucrose and starch as the end product of two gluconeogenic pathways that are physically separated. Which one of the following combination of cell organelles are involved in such physical separation of the process? Number one, sucrose in cytosol and starch in mitochondria. That means it is saying that sucrose is synthesized in cytosol and starch is synthesized in mitochondria. Another option is indicating sucrose in chloroplast and starch in cytosol. Sucrose in mitochondria and starch in cytosol. And fourth option is sucrose in cytosol and starch in chloroplast. So here the correct option is option number 4. Sucrose synthesis occurs in cytosol and starch synthesis occurs in chloroplast, especially in the stroma of the chloroplast. So the fourth option is correct. Second question is on energy transfer in photosynthesis. So energy transfer in the photosynthesis occurs as phycoerythrin, that is electron gets transported from phycoerythrin to phycocyanin, phycocyanin to carotenoid, then to chlorophyll A. Then second option indicates from chlorophyll B to carotenoid, from carotenoid to phycoerythrin, then to chlorophyll A. Third option is saying phycocyanin to phycoerythrin, then to carotenoid, then to chlorophyll A. And fourth option is indicating chlorophyll to carotenoid to phycocyanin and then to chlorophyll A. So the correct sequence of electron flow is the third one, from phycocyanin to phycoerythrin, then to carotenoids and then to chlorophyll A. So let us now come to the third question. Which statement about photosynthesis is false? Now here you have to give stress on this kind of words, whether it is asked that it is true or false. Okay, so you have to identify the false statement from the four statements. So the first statement that is given is the electron carriers involved in photophosphorylation are located on the thylakoid membranes. Then second statement, photosynthesis is a redox process in which water is oxidized and carbon dioxide is reduced. Yes. The enzymes required for carbon fixation are located only in the grana of chloroplasts. In green plants, both photosystem 1 and photosystem 2 are required for the formation of NADPH and H+. Okay, so here out of these, the first, second and the third statement both are correct. Now here the fourth statement is indicating whether the NADPH synthesis requires the involvement of both the photosystems or not. So here only one photosystem is required for NADPH synthesis, that is PS1, or not. Just check it out. So here the third statement is the incorrect one. The enzymes required for CO2 fixation are located in the grana of chloroplast. Actually, they are located in the stroma of the chloroplast, okay, in the thylakoids. So here NADPH will be synthesized only when photosystem 2 and 1 both are operative. Okay, when photosystem 1 is operative, in such case cyclic photophosphorylation occurs, which operates when NADPH levels are high. So under such situation, PS2 will not operate. Then fourth question, why C4 plants show very high rate of photosynthesis as compared to C3 plants? Number one, absence of decarboxylation. Number two, absence of photorespiration. Number three, presence of photorespiration. And fourth option, presence of carboxylation. So here we know that C4 plants have higher productivity, or they have high rate of photosynthesis compared to C3 plants. So why this occurs? Because the C4 plants have very low photorespiration, or you can say it is not detectable. So absence of photorespiration is most appropriate option in this case. So the correct option is second one, absence of photorespiration. Next question, in C4 plants, the source of CO2 during Kelvin cycle is what? C4 or Hatch-Slack pathway. What is the source of CO2 for Kelvin cycle? So whether it is phosphorenol pyruvic acid or pyruvic acid, oxalic acid or malic acid. You just remember that in C4 plants, the decarboxylation of malate occurs to CO2 and pyruvate. Okay, so malic acid is the correct option in this case. Now, very important one, the ratio of CO2, NADPH and ATP for the synthesis of pentose sugar through Kelvin cycle in C3 plants is what? You have to identify the correct options from this. So you have to give stress first on the ratio. What sequence is asked? CNA. That is, you just remember the illogical formula CNA 1, 2, 3. Okay, and what is the product? So pentose sugar, that is C5. So 5 carbons will be required. So 5, 1, 2, 3, multiply all these figures by 5. So 5 is to 2 is to 15 is the correct option. So this is the correct. Okay. So you have to multiply that ratio 1 is to 2 is to 3. 1 is to 2 is to 3 by 5. Okay, so when you multiply it, you will get this ratio 5 is to 10 is to 15. So you have to first find out what is the ratio asked in the question. Photorespiration increases at warm temperature due to ratio of dissolved chloroplast oxygen to CO2 is lower, or ratio of dissolved chloroplast O2 to CO2 is higher, or ratio of dissolved chloroplast O2 to CO2 is not affected, or ratio of dissolved chloroplast O2 to CO2 is equal. So photorespiration occurs when dissolved levels of molecular oxygen in the chloroplast are higher than CO2. Then Rubisco enzyme carries out the oxygenation reaction. So the second option is the most appropriate one, is the correct one. Okay. And again, now the similar question is asked, but here the ratio is different. The ratio of CO2 is to ATP is to NADPH for the synthesis of pentose sugar through Kelvin cycle in C3 plants is what? So I can dial 132 or I can score 132 runs. Okay, CAN 1 is to 3 is to 2. Now, what is the product? Pentose sugar is to be synthesized. Okay, so multiply all the values, all the figures by 5. So 1 is to 3 is to 2. So all the figures when they are multiplied by 5, you will get 5 is to 15 is to 10. Okay. So the most appropriate one is the first option in this case. Okay. So 1 is to 3 is to 2 is the ratio for CO2 is to ATP is to NADPH for Kelvin cycle in C3 plants. Okay. So for synthesis of one pentose sugar, the CO2, ATP and NADPH in this ratio will be required. So this is a very important aspect. You have to remember the ratio and you can use these illogical formulas. You can develop your own illogical formulas also to come to the conclusion. So this was all about the photosynthesis. These are the references which I have used for this presentation. So thank you. So that was all on photosynthesis.
Thank you very much, sir.
Thank you,
I
sir.
think I hope all the participants have got a clarity about photosynthesis and various cycles. And if they have any questions, they will share it in the WhatsApp group, and I will send it to you. Okay.
Okay, sir. Thank you.
Okay. Thank you, sir.
Thank you, sir. And best wishes to all the participants.
Yeah.
Thank you, sir.
Okay. So participants, I will share the PPT of all the lectures with you on the WhatsApp group, and along with this, the feedback form and the mock test form link with you. Okay, so fill it by today itself. So with this, I'm ending this session of the day 4. We will meet you tomorrow. Okay, all the best.